theory of everything. In physics, we've discovered fundamental laws, equations that predict the motion of planets, the behavior of atoms, even the beginning of the universe itself. But each of these laws applies only to part of reality. We have one set for gravity, another for quantum particles, and they don't match. The theory of everything is the idea that there's a single framework, one unified equation that explains it all, every force, every particle, every interaction, from the curve of space-time to the structure of matter. But here's the problem. After decades of searching, we still haven't found it. Einstein's general relativity describes gravity with stunning precision. Quantum mechanics captures the strange behavior of particles at the smallest scales. But when you try to use both, like in the heart of a black hole or the first moment after the Big Bang, the math collapses. Some of the most ambitious theories in modern physics, string theory, loop quantum gravity, grand unification models, promise answers, but none have been confirmed. So the mystery remains. Is nature governed by a single elegant principle we haven't uncovered yet? Or is the universe fundamentally divided? The theory of everything isn't just about unifying physics. It's about discovering whether all of reality follows a hidden code, or if the final piece of the puzzle simply doesn't exist. Universes missing antimatter. According to physics, the universe shouldn't exist, not in the way it does, not with stars, galaxies, or people. In the earliest moments after the Big Bang, matter and antimatter should have been created in equal amounts, and when matter meets antimatter, they annihilate, gone in a flash of pure energy. It's one of the most fundamental interactions we know. So if both were created equally, they should have destroyed each other completely. But they didn't. Somehow, for reasons we still don't understand, there was just a tiny bit more matter than antimatter. Not much, just one extra particle of matter for every billion pairs. But that was enough. When the rest wiped itself out, that tiny imbalance is what survived. That sliver of leftover matter became everything. Every star, every planet, every atom in your body. So where did the antimatter go? Or more precisely, why was there more matter at all? This mystery is known as the Baryon symmetry problem, and it cuts straight to the heart of physics. Some experiments have shown that particles and antiparticles don't behave in perfectly symmetrical ways, a phenomenon called CP violation. But what we've seen so far isn't enough to explain such a massive imbalance. Some theories suggest hidden processes during the Big Bang. Others point to unknown particles or interactions we've never observed. There's even speculation that an entire antimatter universe could exist, separated from ours, forever out of reach. But for now, we're left with a universe that shouldn't be here, and yet somehow is. The missing antimatter is more than just a scientific puzzle. It's a quiet reminder that everything we know is balanced on a mystery we can't yet explain. Fractal universe hypothesis. The universe is vast, immeasurable in scale, stretching billions of light years across space. But what if it wasn't just vast? What if it was infinitely detailed, repeating patterns on every scale, no matter how large or small? This is the strange possibility behind the fractal universe hypothesis. Fractals are patterns that repeat at different scales. Think of a tree. The branches branch out into smaller branches, which branch out into even smaller ones, and so on. The shape looks similar no matter how closely you look. Fractals are everywhere in nature. Clouds, mountains, coastlines, and in mathematics, they represent a form of self-similarity. The fractal universe hypothesis suggests that the entire universe could be a fractal, with similar patterns occurring at every level, from the tiniest particles to the largest galaxies. At first glance, this idea sounds almost too abstract to be real. How could the universe, with all its vast complexity, follow a simple repeating pattern? But some physicists argue that the fractal nature of the universe could help explain some of its most puzzling features. For example, the distribution of galaxies in the universe isn't perfectly uniform. Instead, galaxies form clusters and vast voids that appear somewhat like the branches of a fractal, suggesting a hidden self-similarity across different scales. The most intriguing part of the fractal universe hypothesis is the possibility that, just as fractals never end in complexity, the universe might have no true boundary or end. Instead, it could continue to scale infinitely, with similar structures repeating endlessly as we look deeper into the cosmos, or even deeper into the very fabric of space itself. The idea raises profound questions. Could the universe be a pattern that we have yet to fully comprehend? If the cosmos is indeed fractal, we might be looking at an infinity of universes just waiting to be discovered. The mystery remains unsolved, but the thought alone sparks curiosity about the very structure of everything we know. Emergence of consciousness and physics. What if consciousness, the very thing that allows us to think, feel, and experience the world, could be explained by the fundamental laws of physics? It sounds like the premise of a science fiction story, but some scientists believe that the emergence of consciousness might actually be linked to the underlying workings of the universe. At its core, the emergence of consciousness refers to the idea that complex systems, like the human brain, can give rise to conscious experience through the interaction of simpler components. In other words, consciousness might not be a special property of the mind, but rather something that emerges naturally from the intricate web of physical processes in the brain. But here's the catch. This concept pushes us to wonder, can consciousness be fully explained through the laws of physics alone? Physicists and neuroscientists have been probing this question for decades, and yet the link between the two remains elusive. For centuries, the brain's physical processes, its neurons firing, chemical signals transmitting, have been studied. But the how and why of consciousness, why a brain's activity results in subjective experience, remains a profound mystery. Enter the field of quantum mechanics, where some scientists believe the solution might lie. They propose that the strange behavior of particles at the quantum level could be responsible for the emergence of consciousness. Some theories even suggest that quantum effects in the brain's microtubules, tiny structures inside neurons, may be at the heart of human awareness. This intersection of consciousness and physics raises a mind-bending question. Is consciousness just a byproduct of complex physical interactions? Or is it something more? Could it be that the very fabric of the universe contains the blueprint for consciousness itself? The search for the answers is ongoing, but the mystery remains. Is consciousness just another physical phenomenon, or is it something that transcends the known laws of physics? Cosmic inflation instability. At the very beginning of the universe, something incredible happened. In a fraction of a second, the entire cosmos expanded at an unimaginable rate. This event, known as cosmic inflation, set the stage for everything we see today. But there's a hidden mystery about this expansion. Could the very process that created the universe also lead to its instability? Cosmic inflation is the theory that, just after the Big Bang, the universe expanded exponentially, faster than the speed of light. This rapid expansion smoothed out the universe, creating the uniform structure we observe in galaxies and stars. It's a widely accepted part of cosmology, but there's an unsettling twist to this theory. Inflation may not be as stable as we think. Some scientists believe that the process of inflation could, in theory, trigger an instability in space-time. This instability could cause regions of the universe to undergo another burst of rapid inflation, creating new pocket universes or altering the very fabric of our own universe. These pockets could exist independently of our universe, each with their own set of physical laws and properties, potentially making our universe just one bubble in a vast cosmic foam. But if this instability exists, it raises a chilling question. Could it ever affect us? If the bubble of our universe pops or shifts, what happens to everything inside it? While this is purely speculative at this stage, the idea that our universe might not be as stable as it appears adds an eerie layer to the story of cosmic inflation. The mystery of cosmic inflation instability isn't just about understanding the universe's past. It's about exploring whether our existence might be more fragile and more connected to the deeper workings of the cosmos than we ever realized. The arrow of time paradox. We move through life from past to present to future, always feeling the flow of time. But what if that flow isn't as simple as it seems? What if the arrow of time, the direction in which time flows, isn't as straightforward as we think? The arrow of time. Paradox is one of the most perplexing mysteries in physics. It refers to the idea that time has a definite direction. Things happen in one order, from past to present to future. We remember the past, not the future, and we see objects break down, like a glass shattering, but never spontaneously reassemble. This one-way flow of time seems natural to us, but it poses a big question. Why does time seem to move in only one direction? In physics, the laws of nature, like those of motion or gravity, don't actually dictate a specific direction for time. The fundamental laws are time-symmetric, meaning they could work the same way whether time is moving forward or backward. So why then does time always seem to move forward? Why do we never experience a moment where time flows backward, reversing decay and chaos? The answer seems to lie in a concept called entropy. Entropy is a measure of disorder. As time passes, systems tend to move from order to disorder, like ice melting into water or a room getting messier. This increase in entropy provides a kind of arrow pointing time in one direction, forward. But here's the strange part. While this explains why time feels one way, it doesn't solve the deeper mystery of why time itself is tied to entropy in the first place. The arrow of time paradox keeps scientists searching for answers. It's a question not just about the physics of time, but about how we experience reality. Could the flow of time be more mysterious than we think? The answer remains elusive, pointing to even deeper questions about the nature of the universe itself. Vacuum decay. Imagine the universe as a calm, stable place where everything seems to follow predictable rules. But what if that stability could suddenly collapse without warning, changing everything we know in an instant? This unsettling possibility is known as vacuum decay, and it's one of the most mysterious and mind-bending concepts in modern physics. Vacuum decay is a theoretical event that could happen at any moment, though scientists believe it's highly unlikely. The idea is that our universe, which seems stable, may not be in its lowest energy state. Picture it like a marble sitting at the bottom of a bowl. If the marble moves, it stays at the bottom, resting in the lowest point. But what if the bowl itself was unstable, and the marble could fall into a completely different, deeper state, one that destroys everything in the process? In physics, this deeper, unstable state is called a false vacuum. According to quantum field theory, The vacuum of space isn't truly empty. It's filled with energy. But this energy could be in a false state, which isn't the absolute lowest energy possible. If the universe were to shift from this false vacuum to a true vacuum, it would trigger a chain reaction, changing the laws of physics as we know them, and possibly wiping out the current structure of space and time. The most unsettling part: vacuum decay could happen without warning. It's not something we could see coming, and when it does happen, the shift would spread at the speed of light, obliterating everything in its path. While this sounds like science fiction, scientists have taken it seriously, as it's based on real principles of quantum mechanics. Luckily, vacuum decay is extremely unlikely to occur anytime soon. But the very possibility challenges our understanding of the universe's stability and leaves us with one eerie question: is the universe really as stable as it seems? Phantom energy. In the vastness of space, something strange is happening. Something invisible, yet incredibly powerful. Scientists call it phantom energy, and it might just hold the key to one of the greatest mysteries of the universe. Phantom energy is a mysterious force that seems to be accelerating the expansion of the universe. While we've known for years that the universe is expanding, the surprising twist is that it's expanding faster and faster, not slowing down as we once thought. This mysterious acceleration is driven by dark energy, a force that makes up around 70% of the universe. But phantom energy takes it a step further. It's a form of dark energy that could be even more potent, causing the universe's expansion to speed up at an ever-increasing rate. The concept of phantom energy raises an eerie possibility. What if the universe is expanding so fast that galaxies and stars will eventually be pulled apart, unable to interact with each other ever again? It's as if the fabric of space itself is ripping apart, and phantom energy could be the force driving that catastrophic change. Scientists are still trying to understand how phantom energy works. It might be related to a phenomenon known as the cosmological constant, a term introduced by Albert Einstein in his equations for general relativity. However, phantom energy suggests that the rate of acceleration could continue to increase indefinitely, leading to a scenario called the Big Rip, where the universe tears apart at the seams. The mystery of phantom energy leaves us with more questions than answers. Is it a temporary phase in the universe's life, or will it eventually lead to a dramatic and irreversible end? As scientists study the behavior of dark energy and phantom energy, they're uncovering a hidden force that could change everything we think we know about the universe's fate. Great Attractor mystery. Out in the vastness of space, everything is moving: galaxies, stars, planets. But there's one strange force pulling the entire universe toward a single, mysterious point. This point is known as the Great Attractor, and its influence has baffled scientists for decades. The Great Attractor is a massive gravitational anomaly, located in a part of space we call the Laniakea supercluster, the vast region of galaxies that includes our own Milky Way. But here's the mystery. No one knows exactly what the Great Attractor is. It's hidden behind the zone of avoidance, a region of space where our view is blocked by the dense plane of our galaxy. So, even though we can feel its pull, we can't directly observe it. What we do know is that it's pulling galaxies, including ours, toward it at a mind-boggling speed of over 2 million kilometers per hour. Imagine trying to escape a force so powerful that it drags entire galaxies through space. But what exactly is causing this pull? Some theories suggest it could be a supermassive black hole at the heart of an enormous galaxy cluster, exerting an immense gravitational force. Others think it could be a collection of galaxies so massive and dense that their combined gravity is distorting space-time itself, but the true nature of the Great Attractor remains elusive. Is it just a massive, unseen object, or is it something more, something that challenges our understanding of the universe? The Great Attractor mystery raises questions about the limits of our knowledge. If it's truly pulling on everything, could there be other, unseen forces lurking in the cosmos, waiting to be discovered? As astronomers continue to study this strange phenomenon, the Great Attractor remains one of the most intriguing and unanswered questions in modern physics. Dark flow. In the vast stretches of the cosmos, galaxies are usually drifting apart, moving away from each other as the universe expands. But what if something mysterious was causing them to move in a completely unexpected direction? This is the strange phenomenon known as dark flow. Dark flow was first noticed in 2008 when scientists observed that galaxies, particularly those in the farthest reaches of the observable universe, weren't just following the expected patterns of cosmic expansion. Instead, they seemed to be moving toward a specific point in space. The motion didn't fit with our understanding of the universe's expansion, and scientists were left scratching their heads. What was causing this strange movement? The most fascinating thing about dark flow is that it doesn't seem to be caused by any known force, like gravity from nearby galaxies or clusters. Some believe it's a sign that there's a massive structure in the universe, something too far away to be detected with current technology, that's pulling everything toward it. This unseen force could be a supermassive galaxy cluster or some other form of cosmic structure, one that challenges our understanding of how the universe operates on the largest scales. What makes dark flow even more mysterious is that it could suggest the existence of regions beyond the observable universe, areas that are outside the reach of our current technology. This opens up tantalizing possibilities. Could there be unknown forces, unseen galaxies, or even entire universes beyond our perception? Dark flow raises the unsettling idea that there's much more to the universe than meets the eye, a force beyond our current understanding, pulling galaxies in ways we cannot fully explain. As scientists continue to probe this mystery, it's clear the universe still has many secrets waiting to be uncovered. Supervoid in Eridanus. Imagine staring out into the universe, expecting a vast sea of galaxies and stars, only to find an eerie, empty void, an enormous gap where there's almost nothing. This is what scientists discovered when they stumbled upon the supervoid in Eridanus, one of the largest known voids in the universe. The Eridanus supervoid is a massive, almost incomprehensible emptiness in space. Stretching across a mind-boggling 1.8 billion light-years, it's an area where very few galaxies exist, creating a cosmic desert. But what's truly mysterious about this void is what it might be hiding. While we can see that it's largely devoid of matter, the question remains, what's causing such a large area of space to be so empty? The most intriguing part of the supervoid is its strange effect on the cosmic microwave background radiation, the faint afterglow of the Big Bang. When scientists measured this radiation, they found that the supervoid seemed to be distorting it. The temperature in this region is slightly lower than in other areas, suggesting that the void could be influencing the way energy behaves across vast distances. Some theories suggest that this void is a result of gravitational effects, like massive structures outside of the void pulling on the fabric of space. Others wonder if there's a more mysterious explanation, perhaps tied to the very nature of dark energy or the structure of the universe itself. The supervoid in Eridanus challenges what we know about the cosmos. It's a cold, seemingly lifeless region, but its very existence forces us to ask deeper questions about the shape, structure, and fate of the universe. What might lie beyond our understanding in this cosmic emptiness? The answers remain a fascinating, unsettling mystery. Bubble universes' collision evidence. In the vastness of the cosmos, the universe we know is just one of many possible worlds. What if, hidden in the fabric of space, there are other universes, each a bubble floating alongside ours? And what if these bubble universes actually collided? This is one of the most mind-bending mysteries in modern physics, the possible evidence of bubble universes colliding. The idea of bubble universes comes from a theory called eternal inflation. This theory suggests that after the Big Bang, the universe didn't just expand uniformly. Instead, parts of space began to inflate rapidly, forming different bubbles of space-time. Each bubble could have different laws of physics, different constants, and even different dimensions. Some of these bubbles might still be growing today, while others could have already popped or merged with others. In 2007, scientists thought they might have found evidence of a bubble universe collision. They noticed unusual patterns in the cosmic microwave background, the faint afterglow of the Big Bang, that seemed to be the result of a massive impact. These anomalies, like strange hot or cold spots in the radiation, could be signs that another universe had collided with our own bubble, leaving a trace of the event in the fabric of space itself. The mystery lies in what this could mean for our understanding of the universe. If these bubbles really exist, it suggests that our universe might not be the only one. The discovery of a collision would point to a vast, multi-universe reality, where other universes are not only real, but capable of interacting with each other. The idea of bubble universes colliding challenges everything we know about space, time, and existence itself. While the evidence is still debated, it's a mystery that leaves us wondering, are we just one bubble in an infinite ocean of universes waiting to collide with the unknown? Cold spot in the cosmic microwave background. When scientists first mapped the cosmic microwave background, CMB, the faint glow left over from the Big Bang, they were expecting to find a smooth, uniform sea of radiation. But what they found in 2004 was something much more mysterious. A vast cold spot, an area in space where the temperature of the CMB was noticeably lower than everywhere else. This cold spot, larger than expected, raised an eerie question. What could explain this strange anomaly? The CMB is often referred to as the afterglow of the Big Bang, providing a snapshot of the early universe. It's a key tool in understanding the universe's origins and evolution. So, when researchers saw this cold spot, they were puzzled. The spot appeared to be a significant dip in temperature, and at first, it seemed like a simple statistical anomaly. But as more data came in, scientists began to wonder if something more unusual was happening. Some researchers have suggested that the cold spot could be the result of cosmic inflation, a rapid expansion of the universe right after the Big Bang. But the true mystery remains. Could this cold spot be evidence of something much more mind-boggling, like the influence of a parallel universe? Some theories propose that this anomaly might be the result of a collision between our universe and another, a bubble universe that impacted our own in the distant past, leaving a mark in the cosmic background radiation. While the cold spot has been studied extensively, no one is entirely sure what caused it. Some think it might just be an unexpected variation in the universe's early stages, while others continue to explore its more fantastical explanations. Regardless of its origin, the cold spot remains one of the most intriguing puzzles in cosmology, inviting scientists to rethink the very fabric of our universe, and perhaps the possibility of other realities beyond our own. the axis of evil. In the quest to understand the origins of the universe, scientists have turned to the cosmic microwave background, CMB, the faint afterglow of the Big Bang. It holds the key to many mysteries, revealing details about the universe's earliest moments. But in 2005, astronomers uncovered something unexpected in this ancient radiation. A strange alignment, a phenomenon that would come to be known as the axis of evil. The CMB is typically uniform, spread evenly across the sky, as you'd expect from an event as massive as the Big Bang. But the axis of evil presents a baffling anomaly, an unusual alignment of temperature fluctuations across the sky. These fluctuations don't seem random. Instead, they are strangely oriented along a specific axis, as if some invisible force is pulling at the fabric of space itself. What's so eerie about this discovery is that the alignment appears too perfect to be a coincidence. It goes against predictions from the widely accepted cosmic inflation theory, which suggests that the universe should be much more isotropic, that is, uniform in all directions. Some scientists have even proposed that this alignment could be caused by an unknown systematic error in measurement, but it's difficult to explain why this would occur on such a large scale. Other, more speculative theories suggest that the axis of evil could be evidence of something much deeper, perhaps a connection between our universe and another. Some have even hinted at the possibility that this could be a sign of something outside the standard model of cosmology, challenging our very understanding of the universe. While the mystery of the axis of evil remains unsolved, it continues to haunt physicists. It's a reminder that, even in our most fundamental observations, there's still much about the universe that we don't fully understand, and what we find next might change everything. White holes. In the vastness of space, black holes are famous for their gravity, pulling everything in, even light. But what if there were the opposite, an object that expelled matter and energy instead of swallowing it? This is the strange concept of a white hole. White holes are theoretical objects in physics, first predicted by the equations of general relativity, the same theory that describes black holes. While black holes have event horizons, boundaries beyond which nothing can escape, white holes would have the opposite, a boundary from which nothing can enter. Instead, they would spit out matter and energy, possibly forming a kind of cosmic fountain. The idea of a white hole arises naturally from the mathematics of black holes. In fact, if you reverse the flow of time in a black hole's equations, you get a white hole. While a black hole pulls things inward, a white hole pushes things outward, creating a paradox. How can matter and light escape from a region that, according to general relativity, should be entirely closed off? Here's the mystery. While black holes have been observed directly in the cosmos, no one has ever detected a white hole. That raises a big question. Do they really exist, or are they just mathematical curiosities? Some theories suggest that white holes could be linked to wormholes, connecting distant parts of the universe, or even acting as portals to other universes. In some models, white holes are thought to be the other end of black holes, where matter that falls into a black hole could emerge from a white hole in another part of space. But without any direct evidence, white holes remain one of the most intriguing mysteries in physics, hinting at cosmic possibilities that stretch our imagination. Could they exist in the far reaches of space, or are they simply the product of equations yet to be fully understood? The mystery continues to unfold. Information paradox of black holes. Imagine you drop a book into a black hole. The book is gone, sucked into the abyss, never to be seen again. But here's the strange question that scientists can't seem to answer. Where did the book's information go? This is the information paradox of black holes, one of the most perplexing mysteries in modern physics. According to the laws of quantum mechanics, information about a system, like the pages in the book, can never truly be lost. It's always there, even if we can't see it. But black holes seem to break this rule. When something falls into a black hole, it appears to vanish completely. The black hole absorbs it, and any trace of its original state is gone. This creates a huge problem because, in the quantum world, this violates the principle of unitarity, which says that information should always be preserved. This paradox has baffled physicists for decades. On one hand, we have the well-established laws of quantum mechanics, which tell us that information can't be lost. On the other hand, we have the well-understood mechanics of black holes, which seem to erase information completely. This has led to a significant conflict between the two fundamental pillars of physics, general relativity and quantum mechanics. Some theories suggest that the information is somehow encoded on the surface of the black hole in what's called the holographic principle. Others propose that black holes could eventually evaporate over time, leaking out information in a process known as Hawking radiation. While no solution has been confirmed, the mystery of the information paradox forces scientists to rethink the very foundations of reality. Is information truly lost forever in a black hole? Or is there a deeper layer of physics waiting to be uncovered? The answer could change everything we know about the universe. Black hole firewalls. When you think of black holes, you might imagine the point of no return, the event horizon, where nothing, not even light, can escape. But what if crossing that boundary wasn't just a one-way trip? What if, instead, there was a deadly firewall waiting for anyone who dared to enter? This is the unsettling mystery known as the black hole firewall paradox. The concept of a black hole firewall emerged from a theoretical puzzle in physics. According to general relativity, if you cross the event horizon of a black hole, you would experience no special effects. From your perspective, it would be like walking through an invisible boundary, with nothing alarming happening, until, of course, the crushing gravity of the singularity kills you. But in the world of quantum mechanics, things get much stranger. Quantum mechanics tells us that information can't be destroyed, but when something crosses a black hole's event horizon, it's thought to be lost to the universe. This creates a conflict between the fundamental theories of physics. To resolve this, some physicists propose that, instead of a smooth transition, the event horizon is actually a fiery wall of intense energy, a firewall that would instantly incinerate anything that crosses it. The idea of black hole firewalls challenges our understanding of space, time, and gravity. It raises profound questions. If the firewall exists, it would violate the principle of quantum mechanics that says we can't destroy information. But if it doesn't exist, then we're left with the dilemma of how to reconcile quantum mechanics with general relativity. At the heart of this paradox is the tension between how the universe operates at its largest and smallest scales. The black hole firewall mystery still hasn't been solved, but it's a crucial puzzle in the search for a theory that could unify all of physics. What happens when we cross a black hole's event horizon? The answer could reveal secrets about the fundamental nature of the universe itself. Eternal inflation paradox. At the very beginning of the universe, there was a rapid expansion, what we call cosmic inflation. In an instant, the universe grew from subatomic sizes to the vast expanse we see today. But what if this inflation never stopped? What if, instead of settling into a stable state, the universe continued to expand? forever. This is the mystery of the eternal inflation paradox. Eternal inflation is a theory that suggests the process of cosmic inflation didn't end in one big burst, but rather that certain parts of the universe continue to inflate at different rates, creating endless bubbles of space-time. Each of these bubbles could be a universe of its own, potentially with its own laws of physics, constants and structures. Essentially, our universe could just be one of many in a vast, constantly expanding multiverse. But here's where the paradox arises. According to eternal inflation, new universes are popping up all the time, and this ongoing expansion seems to violate what we know about the nature of time and space. If space keeps inflating forever, can we ever truly measure or understand the full scope of reality? The very idea suggests that what we consider to be our universe is just a small bubble in a much larger, incomprehensible system, one that stretches beyond our observational limits. On top of that, eternal inflation brings up a disturbing question. If new universes are continually being created, what happens to the laws of physics that govern them? Can our understanding of gravity, matter, and energy hold up in such an ever-changing cosmos? The eternal inflation paradox is not just a theoretical puzzle, it's a profound challenge to how we think about the beginning, the nature, and the fate of the universe itself. As scientists continue to study this mind-bending concept, they may uncover a far more complex reality than we ever imagined. Universe as a neural network. What if the universe we live in isn't just a collection of stars, planets, and galaxies, but something more, something like a neural network? This mysterious idea suggests that the cosmos might function in ways similar to how our brains process information. A neural network, in the simplest terms, is a system of interconnected units, or nodes, like neurons in the brain, that work together to process and transmit information. It's the basis for how deep learning works in artificial intelligence. Now, imagine if the entire universe operated like this. Billions of galaxies acting as individual neurons in a cosmic network, constantly exchanging information and feedback. This theory isn't about comparing the physical structure of the universe to a brain. Rather, it's about the idea that the universe might process information in a similar way, through complex patterns and connections between seemingly unrelated parts. Some physicists have proposed that the universe's fundamental laws and structures, from quantum particles to the large-scale organization of galaxies, might function as a giant information processing system, much like a neural network learns, adapts, and evolves. The mystery behind this idea is both mind-boggling and intriguing. Could the universe itself be thinking or learning in a way we haven't yet understood? Are the fundamental forces of physics, like gravity or electromagnetism, just the synaptic connections that hold this vast network together? Some even speculate that consciousness itself could be an emergent property of the universe's grand neural structure. While this theory is still highly speculative, it pushes us to think about the universe in a radically new way. One where the universe isn't just a backdrop for existence, but an active, dynamic system that processes information, just like the brain processes thoughts. It's a mystery that invites us to wonder, is our universe learning, evolving, and possibly even aware of its own existence? The holographic universe. Hypothesis. What if everything you see, hear, and feel, the world around you, isn't truly real, but a projection of something more fundamental? This is the eerie suggestion behind the holographic universe hypothesis. Imagine that the universe we live in is like a 3D hologram, a projection on the surface of a cosmic black hole, or another hidden dimension. At first, this sounds like science fiction, but scientists have been exploring a fascinating idea. What if all the complex, three-dimensional reality we experience is just a 3D projection of information stored on a 2D surface, much like a hologram's 3D image is created from 2D patterns? This concept comes from the world of theoretical physics, particularly from efforts to understand black holes and the nature of space-time. In the 1990s, physicists like Juan Maldacena proposed the holographic principle, which suggests that the entire universe could be encoded on a distant, two-dimensional boundary, like the surface of a black hole. Everything inside this boundary, including space and time, could be the result of how the information is stored and processed on the edge. The most mind-bending part? If this hypothesis is true, the entire universe, every star, every planet, every person, could be an illusion, a projection of data stored in a two-dimensional space we cannot directly observe. The mystery lies in how we experience the universe. Why does reality seem so real if it might be a mere projection? Are we living in a simulation, or is our universe just an intricate illusion of fundamental data? While the holographic universe hypothesis is still theoretical, it pushes the boundaries of how we think about reality, space, and existence itself. What if everything we know is just an image on a vast cosmic screen? Pair-instability supernova. In the vast and mysterious depths of space, stars are born, live, and die. But what happens when a star dies in an explosive, yet bizarre way? Enter the pair-instability supernova, one of the most powerful and puzzling events in the cosmos. Most stars end their lives in dramatic supernova explosions, but some of the biggest stars go out with an even greater bang, an event so intense that it challenges our understanding of physics. A pair-instability supernova happens when a massive star, far larger than our Sun, reaches the end of its life. As it burns through its fuel, the core of the star becomes so hot and dense that it creates something unusual: pairs of particles called electron-positron pairs. At extremely high temperatures, these pairs can absorb energy, causing a sudden and dramatic loss of pressure inside the star. The result? The star can no longer hold itself together and undergoes a catastrophic explosion. What makes this explosion so strange is that the star doesn't collapse into a black hole, like many other supernovae. Instead, it completely disintegrates, often leaving nothing behind but a flash of energy and a brief, yet powerful, burst of light. The mystery lies in the fact that pair-instability supernovae are only possible in the most massive stars, those many times heavier than the Sun. This makes them rare and difficult to observe. Even more intriguing is the question of what happens to the elements created in such explosions. These stars create and scatter heavy elements like gold and platinum, which eventually end up enriching the universe, making life possible. The pair-instability supernova offers a glimpse into the violent and mysterious processes shaping the cosmos. It's a reminder that the universe is full of strange and unexplained phenomena waiting to be discovered. Boundary conditions of the universe. The universe is vast, mysterious, and constantly expanding, but there's a question lurking on the edge of scientific understanding. What are the boundary conditions of the universe? In other words, what limits or rules define the boundaries of space, time, and the very fabric of reality? This question is far from simple. We often think of the universe as infinite, stretching endlessly into space. But when scientists dig deeper into the origins and structure of the cosmos, they encounter a fascinating mystery. If the universe is expanding, what is it expanding into? Is there an edge, or does it simply go on forever? And if the universe had a beginning, like the Big Bang, what were the conditions at the very moment space and time began? One theory suggests that the universe might have no boundaries at all. It's not expanding into anything. Instead, space itself is stretching with no edge or center. This idea is tied to the concept of a closed universe, where space loops back on itself like the surface of a sphere. In such a model, if you traveled far enough, you would eventually return to where you started, just like walking around the Earth. But the mystery doesn't stop there. Another question arises from the idea of the multiverse. If there are multiple universes, do they each have their own boundary conditions? Could our universe simply be one bubble in a much larger and more complex cosmos with rules and limits that we can't yet comprehend? These boundary conditions challenge our understanding of space, time, and reality itself. As scientists continue to study the universe's origins, the search for answers to these deep questions could unlock a new chapter in our understanding of existence. The boundaries of the universe, it seems, may be more mysterious than we ever imagined. Exotic vacuum objects. In the depths of space, there are strange objects that defy everything we think we know about the universe. These are exotic vacuum objects, and they could be more mysterious and dangerous than anything we've ever encountered. Exotic vacuum objects are theoretical cosmic phenomena that exist in what we call the vacuum of space. The vacuum, once thought to be completely empty, is actually filled with fluctuating energy. This energy can give rise to unusual and extreme states of matter, such as exotic vacuum objects. But here's the eerie part. We don't fully understand how they work, or even if they exist. The idea is based on vacuum decay, a process where the vacuum of space, instead of being empty, could have different phases or states. Some theories suggest that in the right conditions, these phases could create extremely dense, unstable objects which could potentially grow larger and more powerful, reshaping everything in their path. In some versions of this theory, exotic vacuum objects are like cosmic bubbles of strange matter. These bubbles could grow, engulfing and altering the space around them. Imagine an object that could fundamentally change the laws of physics as we know them, like a black hole that wasn't bound by the usual rules and potentially capable of consuming everything in its path. The mystery is not just about what these objects might be, but how they would behave if they existed. Would they collapse into a black hole? Would they simply disappear? And could they be lurking in the far reaches of space, unseen, just waiting for the right conditions to emerge? While exotic vacuum objects remain hypothetical, their potential to challenge our understanding of the universe is profound. They force us to ask, is space really empty? Or are there hidden, unknown forces at work, shaping the cosmos in ways we can't even imagine? Tachyonic fields. In the vastness of space, physics works under certain rules. Things move at a certain speed. Forces act in predictable ways. But what if there were particles that broke these rules, traveling faster than light itself? This idea is at the heart of the tachyonic field mystery. Tachyons are hypothetical particles that, unlike anything we know, could travel faster than light. The concept was first introduced in the context of quantum field theory, where tachyons were originally imagined as particles with imaginary mass. But what makes tachyons even more intriguing is the idea of the tachyonic field, a field that could exist throughout the universe, with these superspeed particles as its basis. The mystery surrounding tachyons comes from their strange properties. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum. So, if tachyons exist, they would defy this fundamental rule of physics. But the real puzzle isn't just about whether these particles could exist. It's about what their presence could mean for our understanding of the universe itself. Tachyonic fields have also been proposed as a way to explain certain phenomena in theoretical physics, such as the inflationary period of the early universe, where space expanded at an unimaginable rate. Some scientists suggest that these fields could have played a role in that rapid growth, influencing how the universe evolved. The mystery deepens when considering what tachyons might imply about the nature of time and space. If tachyons can move faster than light, could they also move backward in time? Could they hold the key to unlocking time travel or even new dimensions of space? While no one has found concrete evidence of tachyons yet, the idea continues to stir the imagination of physicists, pointing to possible breakthroughs that could shatter the limits of what we know about the universe. It's a mystery that suggests there's much more to the cosmos than we've yet discovered, waiting perhaps just beyond the speed of light. Superluminal galactic jets, in the far reaches of space, where galaxies spin and stars are born, something strange is happening. Scientists have observed superluminal galactic jets, streams of particles shooting out from the centers of galaxies at speeds faster than light. Yes, faster than light. But how can this be possible when, according to Einstein's theory of relativity, nothing can move faster than the speed of light? These galactic jets are powerful, high-energy streams of plasma, often seen emerging from the supermassive black holes at the heart of galaxies. They can stretch across millions of light-years, moving at incredible speeds. Some jets appear to be traveling faster than light itself. But here's the catch. The jets aren't literally moving faster than light in the traditional sense. Instead, their speed is a visual illusion. The mystery arises from the relativistic effect known as Doppler shifting. When objects move close to the speed of light, the light emitted from them gets stretched or compressed, depending on their direction. If a jet is pointing directly toward us, its motion can appear faster than light due to this effect, creating the illusion of superluminal speed. However, the particles in the jet aren't truly exceeding the cosmic speed limit. They're just moving so fast that they distort our perception of their velocity. But even with this explanation, the mystery remains. Why do these jets exist at all? What does their extraordinary energy and movement tell us about the behavior of matter around black holes and the laws of physics in extreme environments? The discovery of superluminal galactic jets challenges our understanding of space, motion, and gravity, reminding us that the universe often works in ways we can only begin to understand. Quasi-stellar objects, quasars alignment. In the dark reaches of the universe, there are objects so distant, so bright, they seem almost otherworldly. These are quasi-stellar objects, or quasars, and they've been a source of wonder and mystery since their discovery in the 1960s. Quasars are incredibly powerful and energetic centers of distant galaxies, where a supermassive black hole is actively feeding on surrounding material. The result? They emit massive amounts of radiation, often outshining the rest of the galaxy combined. But what's truly baffling about quasars is their strange alignment. The fact that many quasars appear to be arranged in unexpected ways, pointing in strange directions, as if they were deliberately positioned. Scientists have long wondered why this alignment exists. Some studies suggest that quasars might not be randomly distributed across the sky, but that they are aligned along specific axes, pointing in a way that seems to defy natural patterns of galactic distribution. This has raised intriguing questions. Could these alignments be the result of a hidden force in the universe, or do they indicate something we don't yet understand about how galaxies and black holes form? One possibility is that quasars might be aligned due to gravitational interactions between massive cosmic structures, such as galaxy clusters or dark matter. These interactions could be influencing the direction in which the black holes in these galaxies are oriented, leading to an observable pattern of alignment. But the mystery deepens when considering that these alignments occur over vast cosmic distances, much larger than the scale of individual galaxies. Could there be something even more fundamental at play? A hidden influence shaping the universe at the largest scales? The alignment of quasars challenges our understanding of the cosmos and suggests that there's much more to discover. Could the universe be more ordered and more connected than we've realized? The search for answers continues. Pioneer Anomaly. In the vastness of space, there's a spacecraft hurtling through the cosmos, heading toward the outer reaches of our solar system. It's called Pioneer 10, and it was launched in 1972 as part of a groundbreaking mission to explore Jupiter. But as the spacecraft traveled further and further, scientists noticed something strange. Despite all expectations, Pioneer 10 was drifting off course, slightly but noticeably. This unexpected shift became known as the Pioneer Anomaly. At first, the anomaly seemed like a simple error. Perhaps the spacecraft's thrusters were malfunctioning, or maybe there was a flaw in the calculations. But after checking and rechecking the data, it became clear that something more mysterious was at play. Pioneer 10 was moving slower than expected, and no known force seemed to explain why. Over time, scientists tried various theories. Some suggested it was due to heat being radiated from the spacecraft, which might push it in an unexpected direction. This was the most widely accepted explanation. But when Pioneer 11, a sibling spacecraft sent out a few years later, showed similar behavior, the mystery deepened. Could there be another explanation, something even more profound? One possibility is that there's a new, unknown force at work in the far reaches of space, something scientists haven't yet accounted for. Could the Pioneer Anomaly be pointing to a gap in our understanding of physics? Some have even speculated it could have something to do with dark matter or dark energy, mysterious forces that make up most of the universe, but remain largely invisible. The Pioneer Anomaly may seem like a small blip in space, but it raises big questions about how well we truly understand the laws of the universe. What could this mysterious force be? And could it lead to discoveries that completely change the way we view space itself? The answer, it seems, is still out there, waiting to be uncovered. Flyby Anomaly. Imagine a spacecraft flying past a planet, using the planet's gravity to gain speed and change its trajectory, a technique known as a gravity assist. The plan is simple. The spacecraft gets a boost without using extra fuel. But over the years, scientists have noticed something strange when they studied the data from these flybys. The spacecraft weren't behaving as expected. They were mysteriously slowing down just a little bit more than they should. This is the mystery of the Flyby Anomaly. It all started in the 1990s, when the European Space Agency's Ulysses spacecraft and NASA's Galileo probe, among others, experienced slight changes in their velocities during flybys. At first, it seemed like a small, insignificant error, perhaps a glitch in the equipment. But when more missions, like Rosetta and Cassini, showed similar unexpected slowdowns, it became clear that something bigger was going on. The anomaly was puzzling. The spacecraft were flying past planets. Their gravitational influence meant to speed them up, not slow them down. After ruling out factors like radiation pressure, errors in measurements, or friction, scientists were left to wonder, what could explain this strange deceleration? Could there be some unknown force at play, or maybe a hidden factor affecting the spacecraft's motion? One theory is that the spacecraft's engines or materials might be releasing small amounts of heat, pushing them in unexpected directions. But the real mystery remains. Is there an unknown force, something we haven't yet understood, that is causing this anomaly? Could it be a deeper issue in our understanding of gravity, or perhaps even hint at the presence of new physics? The Flyby Anomaly continues to intrigue scientists. It's a subtle, yet powerful reminder that even after decades of space exploration, the universe still holds mysteries that challenge our understanding of the fundamental laws of physics. Oumuamua's non-gravitational acceleration. In 2017, astronomers spotted something extraordinary. A mysterious object zooming through our solar system at a speed far greater than anything we had ever seen before. This object, named Oumuamua, was unlike any asteroid or comet we had encountered. But what really caught the attention of scientists was something far stranger. It appeared to be accelerating in a way that defied the usual laws of physics. Normally, objects moving through space follow predictable paths, influenced only by gravity. But Oumuamua's trajectory didn't quite match the expected calculations. As it passed by the Sun, it sped up, but not in a way that could be fully explained by gravity alone. The odd part: no visible tail of gas or dust, something we'd expect if it were a comet shedding material as it moved. It was as though something was pushing it in a direction it shouldn't be going. This non-gravitational acceleration left scientists puzzled. Was it the pressure from sunlight, a possible outgassing of material, or could there be a completely unknown factor at play, something we hadn't considered? Some even speculated that Oumuamua could be an artificial object, perhaps a probe from another civilization, though this remains highly speculative. The mystery deepens when you consider the object's strange shape. Instead of a typical round or irregular asteroid, Oumuamua was cigar-shaped, raising more questions about its origin and structure. Could it be a fragment of something much larger, or is its unusual motion evidence of an entirely new phenomenon in space? Oumuamua's brief visit to our solar system opened up new questions about the behavior of objects in space. While most of its secrets remain locked away, it serves as a reminder that the universe still holds many mysteries, waiting to be uncovered. Quantum biology phenomena. Imagine a world where the rules of quantum mechanics, strange, invisible forces governing the behavior of particles, play a role in the very processes of life itself. This is the fascinating and mysterious field of quantum biology, where the microscopic world of atoms and particles meets the biology of living organisms. Quantum mechanics tells us that particles can exist in multiple states at once. They can teleport between places and even influence each other instantly, no matter the distance. These behaviors seem completely detached from our everyday experiences. Yet, in recent years, scientists have discovered evidence suggesting that quantum phenomena might be occurring in biological systems in ways that were once thought impossible. One of the most intriguing mysteries in quantum biology is the role of quantum coherence in processes like photosynthesis. Plants, as they absorb sunlight, convert it into energy through a process that's remarkably efficient, much more so than any artificial solar panel. Some researchers believe that the plant's molecules might be using quantum coherence to move energy through the system faster than we can explain with classical physics. It's as if the plant is taking advantage of quantum effects to improve its efficiency, an idea that challenges everything we know about biology. Another area where quantum mechanics seems to play a role is in animal navigation. Migrating birds, for example, may use quantum entanglement to sense the Earth's magnetic field, helping them find their way across vast distances. This phenomenon, if proven, would suggest that our understanding of biology and physics is more intertwined than ever. The mystery of quantum biology remains largely unsolved. Could the strange rules of quantum mechanics be influencing the living world in ways we've only just begun to understand? As scientists dig deeper into this enigmatic field, the answers may reveal an entirely new way of looking at life itself. Quantum consciousness interaction. What if the very act of thinking, the consciousness behind your thoughts, could be connected to the strange world of quantum mechanics? It's a mind-bending idea that has intrigued scientists and philosophers alike. The theory of quantum consciousness interaction. At first glance, the brain seems like a classical system, operating according to well-understood biological processes. But some scientists have proposed that quantum mechanics might play a role in consciousness itself. Quantum mechanics, with its weird and counterintuitive rules, describes a world where particles can exist in multiple states at once, or influence each other instantly across vast distances. So, could these strange properties be affecting how our minds work? The theory gained attention through the work of physicists like Roger Penrose and Stuart Hameroff, who suggested that quantum processes might take place in the brain's neurons, specifically in the microtubules, the tiny structures within cells that help them maintain their shape. According to their theory, quantum effects could help explain how the brain processes information, generates thoughts, and experiences self-awareness. What makes this idea even more mysterious is the question of how quantum states could survive the brain's warm, wet environment. Typically, quantum effects only occur in very isolated, controlled systems, like in a laboratory. Yet, if quantum mechanics truly plays a role in consciousness, it could open up new ways of understanding the mind itself. The mystery remains. If consciousness is tied to quantum mechanics, what does that mean for our understanding of reality? Could quantum physics be the key to unlocking the deepest secrets of the mind, or are we simply projecting quantum phenomena where none exist? As research into quantum consciousness continues, we may soon discover that the link between mind and matter is more mysterious and more fundamental than we ever imagined. Quantum retrocausality. Quantum retrocausality is an eerie and perplexing concept in physics that challenges our traditional understanding of time. In the world of quantum mechanics, particles don't follow the straightforward rules of cause and effect we're used to. Instead, they behave unpredictably, existing in multiple states at once, or appearing to be influenced by events that haven't yet happened. Here's where retrocausality enters the picture. In some interpretations of quantum mechanics, it's proposed that actions in the future can influence events in the past. This means that, rather than time flowing in one direction, like an arrow, it could be more fluid, with cause and effect, sometimes working in reverse. One of the most famous experiments that touches on this idea is the double-slit experiment, where particles, such as electrons, behave differently depending on whether or not they're observed. If quantum retrocausality is real, this could mean that the future act of observation influences the particle's behavior in the past, before it even knew it was going to be observed. It's a strange and unsettling idea. If the future can affect the past, then time itself might not be as linear as we thought. Could our understanding of causality be completely wrong? Could we ever test retrocausality in a way that proves it's not just a theoretical oddity? Quantum retrocausality forces us to rethink not only the nature of time, but also the very fabric of reality. If time can loop in this way, the mysteries of the universe might run much deeper than we've ever imagined. And the truth, it seems, could be waiting in the quantum realm, just beyond our current understanding. Quantum immortality. What if, when we face death, it's not the end at all? What if there's a part of us that continues to exist, branching into a new reality? This unsettling idea is the core of quantum immortality, a concept that stretches our understanding of life, death, and the very fabric of the universe. Quantum immortality is based on the strange and mysterious world of quantum mechanics. In quantum mechanics, particles can exist in multiple states at once, and their outcomes can only be determined when they are observed. This concept leads to the many worlds interpretation, which suggests that for every possible outcome, a new universe is created. Essentially, every time a choice is made or a random event occurs, a new branch of reality is formed, with every possible outcome happening in its own universe. Now, imagine a life-threatening situation, like a deadly accident. According to the idea of quantum immortality, when you face death, your consciousness doesn't vanish. Instead, in the many worlds framework, a version of you survives in a parallel universe where the fatal event didn't occur. From your perspective, you continue living, but you might have unknowingly switched to another version of yourself in a different universe where you survive. The mystery behind quantum immortality is that it challenges everything we think we know about life and death. If we live in a multiverse, could we be jumping from one reality to another without ever realizing it? If every near-death experience is just a switch to another universe, does death really exist? Or is it simply a transition to an alternate version of reality? While quantum immortality is still a highly speculative idea, it sparks a deep and eerie mystery about existence. Is death truly final? Or could we, in some form, live on across infinite realities? The answer remains one of the most intriguing and unresolved questions in quantum physics. Quantum suicide. Imagine a scenario where, in a moment of life or death, you could technically choose to survive through the strange rules of quantum mechanics. This is the unsettling premise behind the concept of quantum suicide. At the heart of quantum suicide is the many worlds interpretation of quantum mechanics. This theory suggests that every time a decision or random event occurs, the universe splits into multiple branches. Each possible outcome plays out in its own separate reality. So, if you flip a coin, one version of you will see heads and another will see tails, each existing in a parallel universe. Now let's say you're faced with a life-threatening situation, a gun aimed at your head, with the trigger pulled. Quantum suicide proposes that, according to the many worlds interpretation, instead of simply dying, the universe splits. One version of you dies, but another version survives. From your perspective, you would always find yourself in the surviving reality, never experiencing death. It's as if you jump to the universe where the fatal event didn't occur. The mystery here isn't just in the bizarre idea of death being avoided, but in the question of whether quantum suicide could actually work. If every life or death event leads to a split in reality, does that mean consciousness somehow follows the path where survival is the outcome, ignoring the branches where death occurs? Though a mind-bending concept, quantum suicide raises deep philosophical and scientific questions about life, death, and consciousness. It challenges our understanding of existence and suggests that perhaps, in some sense, death is just another branch in the multiverse, one we may never experience, at least from our own point of view. While the idea remains purely theoretical, quantum suicide remains one of the most chilling and captivating mysteries in modern physics. Quantum Zeno effect. Imagine you're watching a clock, and no matter how long you stare at it, the second hand never seems to move forward. You blink, and somehow, time has stopped, paused, as if reality itself has frozen. This bizarre idea is at the heart of the quantum Zeno effect, a strange phenomenon in quantum mechanics. In the everyday world, we experience time as a smooth, uninterrupted flow. But in the quantum realm, particles don't always behave predictably. In fact, they exist in multiple states at once, until they're observed. The quantum Zeno effect flips this idea on its head. It suggests that if you observe a quantum system often enough, you can actually prevent it from changing. Think of it like this. Imagine a particle that has a 50-50 chance of decaying, like a radioactive atom. Normally, after a certain amount of time, it would decay. But in the quantum world, if you keep measuring the particle, you stop it from decaying. By constantly observing it, you essentially freeze it in place. The more frequently you check, the less likely it is to change, as though you're trapping it in time. This phenomenon sounds almost surreal, but it's been confirmed in experiments involving atoms and photons. What's even more eerie is the possibility that the quantum Zeno effect could apply to larger systems, suggesting that observation itself could have a deeper influence on the nature of reality. Could this effect hint at a deeper connection between consciousness and the quantum world? The mystery deepens when we consider the implications. If time can be paused through constant observation, what does that say about the nature of time, reality, and the very fabric of the universe? The quantum Zeno effect leaves us with a tantalizing thought. Is reality truly as fluid as we think, or can it be frozen by mere observation? Quantum spin liquids. In the microscopic world of particles, things don't behave like we expect. Atoms and electrons, the building blocks of matter, follow rules that seem strange and defy common sense. One of the most puzzling concepts in this world is quantum spin liquids, an unusual state of matter that challenges everything we know about how particles should behave. Normally, when particles like electrons interact, they align in a predictable way, forming a solid or liquid with a clear structure. But in a quantum spin liquid, things get eerily unpredictable. The particles, despite being in a solid-like state, behave as though they're in constant motion, never settling into a stable arrangement. Instead of spinning in a fixed direction, their spins, a fundamental property of particles, keep flipping, even at absolute zero temperature. This bizarre state of matter was first proposed in the 1970s, but only in recent years have scientists begun to uncover experimental evidence that quantum spin liquids might actually exist. They found signs of this strange behavior in certain materials, like copper oxide compounds, which show signs of these fluctuating spins in a way that defies classical physics. What makes quantum spin liquids so intriguing is their potential for new technologies. They could lead to advancements in quantum computing, where bits of information are stored in quantum states, or even create new ways of manipulating magnetic fields. But there's a catch. Because quantum spin liquids are so difficult to observe and study, much of their behavior remains shrouded in mystery. Could quantum spin liquids be the key to unlocking new states of matter, or are we just scratching the surface of a deeper mystery? This strange, ever-moving state of matter could hold the key to understanding the fundamental forces of nature in ways we've never imagined before. Emergence of time from quantum entanglement. Time, something we all experience but understand so little. We watch the seconds tick by, yet when we dive into the quantum world, time becomes far less certain. In fact, there's a fascinating mystery brewing at the intersection of quantum entanglement and the emergence of time itself. At the heart of quantum mechanics, particles can become entangled, meaning their states are linked in such a way that one particle's behavior affects another, no matter the distance between them. It's a bizarre connection, one that seems to transcend the normal limits of space and time. But here's the mystery. If time is something we experience as a constant linear flow, how does it emerge from the strange and disconnected world of quantum mechanics? Some physicists have proposed that time might not be fundamental at all. Instead, they suggest that time could emerge from quantum entanglement, a process where the interconnectedness of particles somehow gives rise to the flow of time we perceive. Essentially, instead of time being a background feature of the universe, it could be the product of how quantum particles interact. This raises an eerie question. If time is a result of quantum interactions, what does that mean for our everyday experience? Could time, as we know it, just be an illusion created by the entanglement of particles? And if time can emerge in such a way, does this suggest that in the earliest moments of the universe, before the first particles formed, time itself might not have existed? This mystery is still far from solved, but it challenges everything we think we know about time. As scientists continue to explore the quantum world, we might just uncover that time is far more mysterious and far more deeply connected to quantum mechanics than we ever imagined. The answer could change the way we understand the universe itself. Negative mass effect. What if, in the strange world of physics, there was a type of mass that didn't behave the way we expect? Imagine an object that, instead of being pulled toward the ground, actually repelled it. This concept is at the heart of the mysterious idea of negative mass. In the universe as we know it, mass is always positive. Objects with mass, whether they're planets, cars, or even atoms, are attracted to each other by gravity. The bigger the mass, the stronger the gravitational pull. But what if there existed a form of mass that behaved the opposite way? What if it had a negative value, causing it to move in a completely counterintuitive direction? Negative mass would defy everything we think we know about physics. If you pushed an object with negative mass, instead of it moving in the direction you pushed, it would accelerate toward you, as if it were being pulled by the force you applied. This would create a bizarre and almost eerie effect, as if the laws of motion were being turned inside out. While scientists have never observed negative mass in the real world, it's not entirely out of the question. Theoretically, certain exotic particles or conditions in the universe might give rise to negative mass. Some physicists speculate that dark energy, the mysterious force responsible for the accelerated expansion of the universe, might be related to negative mass. The mystery of negative mass challenges the very foundation of our understanding of gravity, motion, and the nature of the universe. Could it exist in some hidden corner of the cosmos? Or is it just a strange mathematical curiosity? The concept of negative mass leaves us wondering, if we ever discovered it, would we be able to harness its power, or would it completely rewrite the rules of physics as we know them? Delayed choice quantum eraser. What if the way we observe the universe could change the past? It sounds impossible, but the delayed choice quantum eraser experiment suggests that, in the quantum world, observation might not just affect the present, it could even influence what's already happened. Here's how it works. Imagine a famous quantum experiment called the double-slit experiment. When a particle, like a photon, is sent through two slits, it behaves like a wave, creating an interference pattern on a screen behind it, just like water waves overlap and create ripples. But here's the strange part. If you observe which slit the photon passes through, it behaves like a particle instead, and the interference pattern disappears. It seems as though the act of observation is changing the particle's behavior, even though it happens after the photon has passed through the slits. Now, the delayed choice quantum eraser takes this idea even further. In this experiment, scientists set up a system where, after the photon passes through the slits, they have the option to observe or erase information about its path. The eerie part. Even after the photon has passed through, the choice to erase or observe its path seems to retroactively influence the interference pattern it created. It's as though the photon decides to act as a wave or a particle based on the later decision to observe or erase the information. This creates a chilling paradox. If the future can affect the past, how do we truly understand causality? Does the act of observation create reality, or does it just reveal something that already exists? The delayed choice. Quantum eraser forces us to rethink our understanding of time, space, and the very nature of reality itself, suggesting that the universe is far more mysterious and flexible than we ever imagined. Non-locality without entanglement. In the strange world of quantum physics, particles seem to break all the rules. They can exist in multiple places at once, and can even communicate with each other instantly, no matter how far apart they are. This phenomenon is known as quantum entanglement, one of the most mind-bending aspects of quantum theory. But what if there was a way for particles to be linked across space without being entangled at all? This brings us to an even more mysterious idea: non-locality without entanglement. In the quantum world, non-locality refers to the idea that particles can influence each other instantly, regardless of the distance between them. With quantum entanglement, when two particles are entangled, measuring one affects the state of the other, no matter how far apart they are. This has been observed time and time again, confirming a strange and almost spooky connection between distant particles. But in some experiments, physicists have noticed that this influence might occur without the particles being entangled at all. This discovery challenges our fundamental understanding of space and time. If particles can interact across vast distances, even without being entangled, how does this happen? How does one particle know what the other is doing without any apparent link? Some scientists suggest that there might be a deeper, hidden connection between particles, something beyond our current understanding of entanglement and quantum fields. The mystery of non-locality without entanglement doesn't just raise questions about how particles interact. It forces us to rethink the very fabric of reality. Could the universe be interconnected in ways that don't follow the rules of traditional physics? As researchers continue to investigate this phenomenon, they may uncover secrets about the true nature of space, time, and the universe itself, secrets that are far stranger than we could have ever imagined. Observer effect variations. What if the mere act of observing something could change its behavior? It sounds like science fiction, but in the strange world of quantum mechanics, this is exactly what happens. This is the observer effect, a mysterious phenomenon that suggests reality itself can be influenced by the act of observation. In the classic double-slit experiment, scientists fire particles like electrons through two slits, and they behave like waves, creating an interference pattern on the other side. But when the particles are observed, measured, or checked, their behavior shifts. Instead of acting like waves, they act like particles, and the interference pattern disappears. It's as if the act of looking at them makes them decide how to behave. But here's the twist. This isn't always the case. The mystery deepens when we look at variations in the observer effect. In some experiments, it's clear that observing a particle changes its state, but in others, the change is subtle or even non-existent. Why do some observations seem to collapse the wave function, while others don't seem to have much of an effect at all? Could there be factors we aren't aware of, influencing when and how observation alters quantum systems? Some physicists believe the observer effect reveals deep truths about the relationship between consciousness and reality. Others argue it's just an artifact of how we measure things. Could our understanding of observation and measurement in quantum mechanics be incomplete? Or is there something more profound going on, an unseen connection between the observer and the observed? The variations in the observer effect continue to puzzle scientists, leaving us with more questions than answers. How much does our perception truly shape reality? And could the act of observation itself be altering the very fabric of existence? The answer remains hidden, waiting for us to uncover it. Quantum Cheshire Cat. Imagine you're watching a cat in a box. You look away for a moment, and when you look back, you find the cat's tail in one place and its head in another. It sounds impossible, but this is what physicists call the quantum Cheshire Cat, a bizarre and mind-bending concept from the world of quantum mechanics. The quantum Cheshire Cat is an idea that comes from a strange experiment conducted to test how quantum particles behave. In the experiment, researchers sent particles, like photons, through a device that splits them into different parts. What they discovered was eerie. In a quantum system, the particle and its properties, such as its spin or polarization, could separate. The photon's body would move one way, while its properties, like its spin, moved in a different direction, almost like the Cheshire Cat from Alice in Wonderland, where the cat's smile and body could be separated, leaving only the grin behind. This phenomenon challenges everything we know about objects and their characteristics. In our everyday experience, we expect things to be tied together. If you see a cat, you expect to see its tail and its head as one. But in the quantum world, particles can exhibit this strange disconnection. It raises a big question. If particles and their properties can be separated, how do we truly understand the nature of reality? What does this say about the relationship between an object and its attributes? The quantum Cheshire Cat doesn't just break our understanding of particles, it forces us to rethink how deeply connected reality is, and whether our perceptions of the world are really as coherent as we believe. It's a mystery that hints at the strange, hidden nature of the quantum realm. Could the universe be less solid, less predictable than we've ever imagined? Quantum foam. Beneath the calm, predictable fabric of space and time, there's a mysterious and chaotic world, one so small we can't see it with any of our instruments. This is the world of quantum foam, a bizarre and almost eerie concept in physics that challenges everything we think we know about the nature of reality. Quantum foam is thought to exist at the Planck scale, the smallest possible scale of space and time. At this scale, space is anything but empty. Instead, it's constantly fluctuating, bubbling, and shifting. Imagine the smooth surface of the ocean, but instead of calm water, it's made of tiny, unpredictable fluctuations, foam that appears and disappears on incredibly tiny scales, far smaller than atoms. These fluctuations are what we call quantum foam. The mystery surrounding quantum foam lies in how it fits into our understanding of the universe. At large scales, Space seems smooth and predictable, but at the quantum level, space is constantly jittering, with particles popping in and out of existence. These fluctuations are thought to be so tiny, they can't be directly observed. Yet, they could have a profound impact on how space-time behaves, affecting everything from gravity to the fundamental forces that shape the universe. Quantum foam also holds key insights into the nature of black holes and the Big Bang. Some theorists believe that the incredibly dense and hot conditions at the start of the universe could have been shaped by this quantum foam, setting the stage for the cosmos to evolve. But how exactly these tiny fluctuations could lead to the vast universe we know is still a mystery. The concept of quantum foam is one of the most mind-bending ideas in physics. It suggests that beneath the calm surface of reality, space itself may be far more chaotic and unpredictable than we ever imagined. And as we continue to explore this strange realm, the mysteries of the universe only deepen. The measurement problem. At the heart of quantum mechanics lies a baffling mystery that has puzzled scientists for decades. It's called the measurement problem, and it's one of the most fundamental questions in physics. The mystery is simple. How do we go from the strange, blurry world of quantum particles to the clear, predictable reality we experience every day? In the quantum world, particles like electrons and photons don't have definite positions or speeds. Instead, they exist in a state of probability, meaning they could be in many places at once or have many different speeds until we measure them. It's only when we observe a particle that it decides where it is or how fast it's moving. This is called wave function collapse. But here's the problem. Why does the act of measuring or observing seem to force the particle into one state, while before it existed in multiple possibilities? This leads to a strange paradox. In one sense, quantum mechanics works perfectly well, predicting particle behavior with incredible accuracy. But at the same time, it's hard to explain how or why the act of measurement changes everything. How can something so uncertain, existing in multiple states, become definite simply because we looked at it? The measurement problem raises deeper questions about the nature of reality itself. Does the act of observing the universe actually create the world we experience? Or is there something else happening that we don't yet understand? Some theorists suggest that consciousness itself might play a role, while others propose that the universe follows hidden rules that we have yet to uncover. The measurement problem may seem abstract, but it's at the core of our understanding of the universe. It challenges us to rethink what we know about reality and opens up a mystery that may one day reveal the true nature of the cosmos. Scale relativity. In the universe, everything is connected by scale, from the tiniest particles in an atom to the vast galaxies stretching across space. The laws of physics operate differently depending on the scale you're looking at. But what if the way we understand space, time, and even the fabric of reality itself changes depending on the scale? This is the mysterious concept behind scale relativity. The idea of scale relativity is built on a fascinating question. Do the same laws of physics apply no matter how small or large the system is? In our everyday experience, we see the world as governed by predictable rules. Gravity pulls us down. Objects move in straightforward ways. But at the quantum level, those rules break down. Particles behave in unpredictable ways, existing in multiple states at once. So, what happens when we consider all scales? Tiny subatomic particles, atoms, and the vast universe. Scale relativity suggests that just as Einstein's theory of relativity tells us space and time are flexible on large scales, curved by gravity, there could be similar changes at smaller scales. It proposes that the same principles that apply to the very large might also apply to the very small, but with different effects. In essence, the rules of the universe might not be as constant as we think. They could change depending on the scale, creating a more dynamic and unpredictable reality. One of the most intriguing aspects of scale relativity is that it could provide a bridge between quantum mechanics and general relativity, the two pillars of modern physics that have never been fully reconciled. Could scale relativity offer the key to unifying the way we understand the universe, from the smallest particles to the largest galaxies? The idea remains a mystery, inviting scientists to rethink how the laws of physics work across all scales. The answers may hold the key to understanding the very nature of reality itself. Virtual particles becoming real. In the quantum world, there's a strange phenomenon that seems to defy our understanding of reality. It's called virtual particles, tiny, fleeting particles that exist for only a split second before disappearing. But here's the mystery. Could these virtual particles somehow become real? Virtual particles aren't something you can observe directly. They appear as part of quantum fields, popping in and out of existence, briefly borrowing energy from their surroundings. According to quantum theory, these particles exist in a state of constant flux, like tiny bubbles that form and vanish in a vacuum. Normally, virtual particles are harmless, and they don't last long enough to affect anything on a large scale. But what happens when these ephemeral particles stick around longer than expected? Could they actually become real, with lasting effects on the physical world? The mystery deepens when you consider phenomena like the Casimir effect, where virtual particles seem to cause a real force between two closely placed objects. It's as if these invisible particles are pulling on the objects, creating an observable effect, even though they shouldn't exist for long. More fascinating still, some theories suggest that virtual particles could play a role in the creation of new particles, like in high-energy physics experiments. In these cases, virtual particles could gain enough energy to break free and manifest as real particles, giving rise to new forms of matter. This raises an unsettling question. If virtual particles can become real, does this mean that the line between what's possible and impossible in the quantum world is blurrier than we thought? Are the boundaries of reality more flexible, more fluid than we've ever imagined? The mystery of virtual particles becoming real invites us to reconsider the very nature of existence and challenges us to explore the hidden realms of physics that shape our universe. Bimetric gravity. Gravity, one of the fundamental forces of the universe, has puzzled scientists for centuries. We know how it works on the scale of planets and galaxies, but when it comes to the smallest scales of quantum mechanics, gravity still doesn't quite fit in. Enter bimetric gravity, a mysterious idea that could help solve some of these cosmic puzzles. In the world of general relativity, gravity is understood as the bending of space-time caused by mass and energy. This theory works remarkably well for large-scale objects like stars and black holes. But at the quantum level, where particles and fields interact, gravity doesn't seem to behave the same way. It's as though there's something missing, a piece of the puzzle that prevents the theory from fully explaining everything. Bimetric gravity suggests a possible solution. What if there isn't just one type of space-time in the universe, but two? In this theory, there are two separate metrics, or ways of measuring space-time, interacting with each other. One metric governs the familiar, large-scale effects of gravity that we see with planets and galaxies. The other could govern the tiny quantum world, where particles behave in strange, unpredictable ways. What makes this idea even more intriguing is that it could provide a bridge between the two most powerful theories in physics, general relativity and quantum mechanics. These two theories have never quite meshed, and bimetric gravity might be the key to unifying them. But here's the mystery. Could the existence of these two separate metrics explain phenomena we haven't fully understood yet, like dark matter or the behavior of black holes? If bimetric gravity is correct, it could revolutionize our understanding of the universe, offering a glimpse into how space-time works on both the largest and smallest scales. Bimetric gravity might just be the breakthrough needed to connect the dots in the most fundamental mystery of physics: how the universe really works. Einstein-Cartan Theory. We all know Einstein's theory of general relativity, the groundbreaking idea that gravity is a result of massive objects bending space and time. But what if there's more to gravity than even Einstein realized? What if the fabric of space-time itself could be influenced by something more than mass? This is where the Einstein-Cartan theory enters the picture. A mysterious extension of Einstein's work that could offer new answers to some of the universe's deepest questions. The Einstein-Cartan theory, developed in the 20th century, builds on Einstein's general relativity, but introduces something new: the idea that space-time is also influenced by spin, an intrinsic property of particles. In this theory, gravity isn't just a result of mass-bending space-time, it's also shaped by the spin of particles moving through it. This small but significant addition could explain some strange, unexplained phenomena in the universe. What makes the Einstein-Cartan theory so intriguing is its potential to describe the behavior of matter in extreme conditions, like inside black holes or during the early moments of the Big Bang, where the usual laws of physics seem to break down. By incorporating spin into the fabric of space-time, this theory might offer a better understanding of how gravity works in these mysterious places. But the mystery doesn't stop there. The Einstein-Cartan theory also suggests that torsion, a twisting force in space-time caused by spin, could play a role in the structure of the universe. Could this twisting force help explain the elusive nature of dark matter, or even point to new dimensions we haven't yet detected? The Einstein-Cartan theory might not be the final answer, but it opens up an eerie possibility. What if the universe operates on even deeper principles than we ever imagined, with forces and dimensions we've yet to fully uncover? The theory is still under exploration, and its true potential remains a tantalizing mystery at the heart of modern physics. Double special relativity theory. Imagine a world where the rules of physics shift depending on where you are or how fast you're moving. This is the reality described by special relativity, the theory developed by Albert Einstein, which says that time and space are relative depending on your speed. But what if there's more to the story? What if there's not just one special way to experience space and time, but two? This is the core of the mysterious double special relativity theory, DSR. At its heart, DSR proposes that, in certain extreme conditions, like those near black holes or at the beginning of the universe, both the speed of light and the quantum structure of space-time are special. While special relativity has already taught us that nothing can travel faster than light, DSR takes things a step further, suggesting that the speed of light isn't the only limit. Instead, the structure of space-time itself might behave differently at very small or very fast scales, suggesting that the nature of the universe could be even more flexible than we realize. What makes DSR particularly intriguing is its challenge to our understanding of the fabric of space and time. In Einstein's theory, time and space are treated as a single, unchanging entity. but DSR hints that at extremely high energies or speeds, space and time may behave in ways we don't yet fully understand, possibly revealing new dimensions of reality. Could DSR explain mysteries like the behavior of particles at near-light speeds, or provide insight into the nature of dark energy and dark matter? As researchers continue to explore this theory, we are left with one haunting question. What if the universe, in all its complexity, is far stranger and more layered than we ever imagined? The double special relativity theory challenges us to rethink everything we thought we knew about space, time, and the very fabric of reality. Mass gap problem. In the strange and unpredictable world of quantum physics, there's a perplexing mystery that scientists have been trying to solve for decades. The mass gap problem. Imagine a world where particles are either light, like photons, or incredibly heavy, like protons. But there's a strange gap in between. This gap, where particles should exist but don't seem to, challenges our understanding of the fundamental building blocks of matter. In particle physics, the Standard Model explains how particles interact through forces. It works beautifully for most particles, those with very little mass and those with a lot. But when we look in the middle, we notice something odd. The mass gap is the region where no stable particles seem to fit. This gap, roughly between the mass of a proton and the mass of particles like the Higgs boson, has baffled physicists. This mystery matters because understanding the mass gap could unlock crucial insights into how the universe works at its most fundamental level. Could the gap be hiding new, unknown particles? Some theorists speculate that the solution to this puzzle could be tied to strongly interacting particles, ones that are bound together by the force of nature but have never been observed. If they exist, they could be the key to understanding complex phenomena like dark matter, or even the forces that shaped the early universe. The mass gap isn't just a technical curiosity, it's a window into the unknown. Could this missing link reveal a hidden layer of reality, one that might change our understanding of everything from the tiniest particles to the most powerful forces in the universe? The mystery of the mass gap remains unsolved, but every new discovery brings us closer to uncovering the secrets that lie within. Higgs boson metastability. In 2012, physicists made a groundbreaking discovery at CERN, the Higgs boson, a particle that gives other particles mass. This discovery was a monumental achievement in understanding the universe's basic structure. But hidden in this discovery is a fascinating and unsettling mystery. The idea that the Higgs boson itself could be in a state of metastability, meaning it could one day break down and change the very nature of reality. To understand this, imagine the Higgs field as a smooth landscape that gives mass to particles. In its stable state, it's like a ball resting in a valley. But what if that valley isn't as deep as we thought? What if the ball, representing the Higgs field, could someday roll out of that stable position and into a deeper valley, one that we don't fully understand? This is the essence of the Higgs boson metastability. If the Higgs field were to fall into this new, deeper state, it could trigger a chain reaction that would affect the entire universe. This might seem like pure science fiction, but calculations show that the universe could, in theory, be on the edge of such a collapse. The catch? It would take an immense amount of time, billions of years or longer, before anything drastic happens. The real mystery lies in whether we are living in a stable valley or if we're teetering on the edge of an unstable one. Could the Higgs boson, despite being discovered as stable in our experiments, be hiding a potential for much more? This mystery has serious implications for our understanding of the universe's fate, leaving us with a haunting question. Is the universe as stable as we think? Or are we just one step away from an unforeseen cosmic shift? Axion dark matter experiment results. For years, scientists have known that most of the universe's mass doesn't seem to be made up of ordinary matter, the stuff we can see and touch. This mysterious invisible mass is called dark matter, and it makes up about 85% of the total mass in the universe. But here's the catch. We still don't know what it is. One of the leading theories suggests that dark matter could be made of tiny elusive particles called axions. But despite years of searching, these particles have remained elusive until now. In recent experiments, scientists have begun to close in on this mysterious axion. Axions are theoretical particles that are so small and weakly interacting that they could explain the dark matter we can't see. They are predicted to be light, stable, and capable of interacting with electromagnetic fields, but only under very specific conditions. Their discovery would be groundbreaking, offering an explanation for dark matter that could change everything we know about the universe. The mystery deepened when the results of a key axion dark matter experiment came in. After months of searching for signs of axions, researchers found hints, unexplained signals that could be related to the behavior of these elusive particles. While they haven't definitively identified axions yet, these signals are intriguing, hinting that we might be on the edge of uncovering a new realm of physics. The mystery remains. Are these signals truly the elusive axions, or is something else at play? Could this be the breakthrough that finally explains dark matter? Or is there still more to discover? As researchers continue to dig deeper, the axion dark matter experiment brings us one step closer to understanding the hidden forces that shape our universe. The search continues, and with it, the potential to rewrite our understanding of reality itself. Chameleon particles. Imagine particles that can change their identity depending on where they are, almost as if they were hiding in plain sight. This is the mystery of chameleon particles, one of the most perplexing ideas in modern physics. Chameleon particles are theoretical particles that, like the animal they're named after, can change their properties based on their surroundings. In theory, these particles would interact more strongly in environments with high energy, but become almost undetectable in low-energy areas, like our own space. This ability to adapt makes them incredibly elusive, which is why they've remained so mysterious. The concept of chameleon particles emerged from attempts to explain dark energy, the mysterious force accelerating the expansion of the universe. Chameleon particles are hypothesized to be a possible explanation for dark energy, because just like dark energy, they could have a varying influence depending on where they are. In areas with a lot of mass, like near galaxies or clusters of galaxies, these particles might interact more strongly, giving us clues about how the universe works on a large scale. But in empty space, where there's little mass, they would almost vanish, making them incredibly difficult to detect. The mystery deepens with the implications. If chameleon particles do exist, they could change our entire understanding of space, energy, and gravity. They might even be the key to explaining why the universe's expansion is speeding up. Despite extensive efforts, no one has yet been able to detect chameleon particles. But the very idea raises eerie questions about the universe, about hidden forces we cannot see, and particles that could be all around us, undetected, waiting to reveal their secrets. Could these elusive particles be the missing link in the puzzle of dark energy? Or are they just a fascinating mystery waiting to be uncovered? Gran Sasso faster-than-light neutrinos. In 2011, something extraordinary happened deep underground in Italy. Scientists at the Gran Sasso laboratory, part of the opera experiment, observed something that made the physics community stop in its tracks. For a brief moment, neutrinos, particles that are famously difficult to detect, appeared to be traveling faster than light. If true, this discovery would have shattered one of the most fundamental rules of physics. Einstein's theory of relativity, which states that nothing can move faster than light. Neutrinos are extremely small, almost massless particles that can pass through matter as if it doesn't exist. They're notoriously hard to study, but this experiment seemed to show them doing something far more extraordinary than anyone expected. When the team at Gran Sasso sent a beam of neutrinos from CERN, about 730 kilometers away, they recorded an unsettling result. The neutrinos arrived faster than the speed of light. The implications were huge. If these findings were correct, it would challenge everything we know about space, time, and the limits of the universe. Scientists scrambled to confirm the result, but doubts quickly arose. Could it be a mistake? After all, if this were true, it would turn physics as we know it upside down. Further investigations into the data eventually revealed an error in the timing equipment. When corrected, the anomaly disappeared, and the neutrinos were back within the bounds of relativity. The mystery was solved, or was it? While the faster-than-light neutrino phenomenon turned out to be a mistake, the fact that such an observation seemed possible raised deeper questions about the limits of our current theories. The Gran Sasso neutrino anomaly serves as a reminder of how fragile our understanding of the universe can be, and how easily new discoveries could change everything we think we know about the nature of reality. Neutrino flavor oscillation. Deep beneath our everyday experience, neutrinos, tiny, nearly invisible particles, are playing a baffling game of hide and seek with scientists. The mystery behind neutrino flavor oscillation is one of the most intriguing puzzles in particle physics, and it could hold the key to understanding the very nature of these elusive particles. Neutrinos come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Traditionally, we thought that once a neutrino was produced in a specific flavor, it would remain that way forever. But, to everyone's surprise, in the late 1990s, scientists found evidence that neutrinos could actually change or oscillate between these flavors as they travel through space. In other words, a neutrino that starts as one flavor might transform into a different flavor as it moves along. This was a complete surprise because it suggests that neutrinos have mass, something that was once thought impossible for such tiny particles. This discovery has profound implications for our understanding of the universe, particularly in areas like particle physics and cosmology. What's even more baffling is how these flavor oscillations happen. Scientists have been working on experiments to track neutrinos over long distances, like those coming from the Sun or even from distant supernovae. Yet, the mechanism behind why or how these oscillations occur remains shrouded in mystery. Why would a particle with such a tiny mass behave this way? Could there be hidden forces at play that we don't yet understand? The mystery of neutrino flavor oscillation challenges everything we thought we knew about the fundamental particles that make up the universe. The more we uncover, the deeper the questions go. Could understanding neutrinos unlock answers about the very origins of matter, or even the fate of the universe itself? The search continues, and the mystery remains. Lorentz Violation. Imagine a world where the very fabric of space-time doesn't behave the way we think it should. A world where the speed of light is no longer constant, and the rules that govern how things move and interact are subtly and profoundly different. This is the mystery of Lorentz Violation. For over a century, Einstein's theory of special relativity has stood as one of the cornerstones of modern physics. It tells us that the speed of light is always constant, no matter where you are or how fast you're moving. This principle is so ingrained in our understanding of the universe that it shapes everything from GPS technology to our understanding of space travel. But what if that constant, unchanging speed of light isn't quite so unchanging after all? Lorentz Violation suggests just that. What if the laws of physics could break down in certain extreme conditions, allowing for the possibility that the speed of light might vary depending on where you are in space-time? Could there be hidden forces or unknown physics operating at scales we haven't yet explored? The mystery began when scientists detected small but intriguing anomalies in high-energy particles. These particles seemed to behave in a way that didn't fully fit the predictions of relativity, suggesting that space-time could be subtly bent or altered, and the speed of light could vary under certain conditions. Experiments looking for signs of Lorentz violation have focused on things like cosmic rays and particles moving at speeds close to the speed of light, where these violations might reveal themselves. Lorentz violation could be the key to unlocking a deeper understanding of the universe, possibly connecting the strange world of quantum mechanics with the vastness of relativity. It raises an eerie question. What if our understanding of space-time is only a shadow of the true reality, one that exists beyond the limits we can currently perceive? The search for answers continues, and with it, the promise of revealing new hidden layers of the universe. Muon anomaly. In a world where the fundamental rules of physics are tightly woven together, one curious anomaly has been making scientists take a closer look. This is the Muon anomaly, also known as the Muon G-2 experiment, and it might just be hinting at something bigger, something that could challenge the very laws of physics as we know them. Muon particles are like the cousins of electrons, familiar in many ways, but heavier and unstable. In 1961, scientists noticed something strange about how muons behave in magnetic fields. They expected the muon's magnetic properties to align perfectly with the established laws of physics. But when they measured how muons spin, they found a slight discrepancy. Something wasn't quite right. Fast forward to the 2000s, and experiments at places like Fermilab in Illinois began testing this anomaly more carefully. Scientists started comparing the behavior of muons with the predictions from the Standard Model, the theory that describes how particles interact. To their surprise, the muons didn't quite follow the expected pattern. They were wiggling in a way that didn't match the laws they thought governed their behavior. This discrepancy, this anomaly, could indicate that there's something beyond the Standard Model, a hidden force or particle we haven't yet discovered. The mystery deepens when you consider what this anomaly might be pointing to. Could the muon anomaly be the first sign of new physics, revealing the presence of unknown particles or forces? Some theorists suggest it could be connected to dark matter or even new dimensions of space-time, things we've only speculated about. While the Muon G2 results have scientists buzzing with excitement, the mystery isn't solved yet. Could this small difference in behavior lead us to a whole new understanding of the universe? The search continues, and with it, the possibility of breaking open new chapters in physics. Gravitational anomalies on Earth. On Earth, gravity is usually a constant force. It pulls us down, keeps the oceans in place, and governs the movement of everything from apples to planets. But in certain places on our planet, gravity behaves in strange and unexpected ways, one of the most puzzling being the Hudson Bay anomaly. This anomaly, located in Canada near Hudson Bay, has baffled scientists for years. What makes it so strange is that measurements of Earth's gravitational pull in this region are weaker than expected. In fact, the gravitational pull here is significantly lower than surrounding areas, as if something is missing beneath the surface. Initially, scientists suspected that this could be due to a simple geological reason, perhaps a lack of dense rock in the area. But the more measurements were taken, the more it became clear that there was something far stranger going on. The anomaly doesn't fit neatly into any geological explanation. One theory suggests that the anomaly could be related to ancient processes in Earth's history, possibly a remnant from a time when the continent was much different. Another possibility is that the anomaly might be linked to the Earth's mantle dynamics, how the Earth's interior behaves, especially in the long term, but no one can say for sure. What makes the Hudson Bay anomaly particularly eerie is that some theories propose that it could also be related to the behavior of dark matter, the mysterious invisible substance that makes up a large portion of the universe's mass. Could dark matter, with its elusive properties, be affecting the Earth's gravity in unexpected ways? This unexplained gravitational anomaly at Hudson Bay invites us to rethink our understanding of gravity and the forces shaping our planet. Is there a hidden, unseen force at work beneath the surface? The mystery continues to unfold, leaving scientists with more questions than answers about the very fabric of our planet. Earth's hum. Have you ever heard a strange, low-frequency hum and wondered what could be causing it? It's not just your imagination. For years, people all over the world have reported hearing an eerie, continuous sound, a sound that has no obvious source. This phenomenon is known as the Earth's hum, or more formally, the unexplained Earth oscillation, and scientists are still trying to figure out what's behind it. The hum is a low-frequency vibration, typically around 10 Hz, and it's not something most people hear consciously, but some can feel it or hear it faintly, especially in certain regions. It's been recorded in cities, remote areas, and even the deep ocean. Oddly, it's not always constant. Sometimes it seems to come and go without any clear pattern, making it all the more puzzling. For years, scientists have tried to explain the hum, but they've had no luck pinpointing its exact cause. One possibility is that it's linked to tectonic activity, the movement of Earth's plates. Some researchers suggest that the vibrations could be caused by seismic events, too small to detect as earthquakes, but still enough to create these vibrations. Others think it could be tied to atmospheric phenomena, like wind patterns or ocean waves, creating low-frequency sound waves that travel long distances. What's even more mysterious is the suggestion that the hum could be tied to human-made activities, like industrial processes or traffic. Yet many of the strongest recordings of the hum seem to happen in remote, quiet places. Could the Earth itself be singing, sending out vibrations we've never fully understood? Or is there a hidden, unseen force, natural or man-made, that's shaping these mysterious oscillations? The Earth's hum remains one of the most unsettling and intriguing mysteries, leaving us to wonder if it's simply a natural occurrence or something more profound lurking beneath the surface. Ball lightning formation. Imagine a stormy night when the sky cracks open with lightning. Suddenly, a glowing, floating ball of light appears, hovering in the air, moving erratically, and then vanishing just as mysteriously as it appeared. This strange phenomenon is known as ball lightning, and it's one of the most elusive and baffling occurrences in atmospheric science. Ball lightning has been reported for centuries, but scientists still don't fully understand what causes it. Unlike regular lightning, which we can predict and measure, ball lightning seems to defy the rules of physics. These glowing orbs can range in size from a small ball to something as large as a basketball, and they can last from a few seconds to a minute. Sometimes they move around, other times they float still, and occasionally they even pass through solid objects like windows, leaving observers in awe and often fear. The mystery begins with how these balls of light are formed. Some theories suggest they're created by electrical discharges during thunderstorms, but what's truly puzzling is how they manage to persist and move without simply dissipating. Some researchers believe that ball lightning might be a form of plasma, a state of matter that can conduct electricity, but how this plasma remains stable for long enough to form a visible, floating ball is still unknown. Another theory involves the interaction of lightning with materials in the environment, like the Earth's magnetic fields, or even unusual chemical reactions that happen in the atmosphere. But despite several attempts to recreate ball lightning in labs, scientists have never successfully produced it under controlled conditions. The mystery of ball lightning remains unsolved, leaving us to wonder, could there be hidden forces in nature that we've yet to fully understand? What if the key to this eerie phenomenon could unlock new insights into the nature of energy, electricity, and the very fabric of space itself? Electromagnetic anomalies at Hessdalen Valley. In a remote valley in Norway, something strange happens in the night sky. For decades, researchers have been investigating electromagnetic anomalies in Hessdalen Valley, where mysterious lights appear in the sky, glowing and moving in ways that defy conventional explanations. These lights, often called Hessdalen lights, have puzzled scientists and locals alike. The mystery starts with the nature of these lights. Sometimes they appear as bright, stationary orbs. Other times they move erratically, darting across the sky in ways that suggest a kind of intelligence or pattern. The lights have been observed for over a century, but despite numerous attempts to understand them, no one has been able to pinpoint their exact cause. One of the leading theories is that these lights might be connected to electromagnetic phenomena. The region's unique geography, including its proximity to certain mineral deposits, could create the perfect conditions for electromagnetic fields that produce these glowing lights. Some researchers believe they could be the result of ionized particles in the air, possibly influenced by the Earth's magnetic field or local electrical charges. However, no one has been able to explain why these phenomena happen so consistently in Hessdalen, yet not in other parts of the world. The mystery deepens when you consider the possibility of something far more unusual. Could the lights be a manifestation of unknown forces, perhaps related to dark energy or some yet undiscovered phenomenon in the Earth's atmosphere? Could they be tied to a hidden form of energy, or even a different way that electromagnetic fields behave under specific conditions? Hessdalen Valley's electromagnetic anomalies remain one of the most intriguing mysteries in modern physics. As scientists continue their investigations, they're left with an unsettling thought. What if these unexplained lights are just a glimpse into forces beyond our understanding, hiding in the very air around us? Spontaneous human combustion. It's a mystery that has fascinated and terrified people for centuries. Spontaneous human combustion. The inexplicable phenomenon where people seem to suddenly burst into flames without any external ignition source. The cases often involve a person being found severely burned, sometimes even to the point of complete destruction, while the surroundings remain relatively untouched. But is this strange event even possible from a scientific standpoint? What could physics say about these bizarre occurrences? Spontaneous human combustion seems like something out of a horror movie, but there are real reports of such incidents throughout history. Some theorists suggest that chemical reactions in the body might be the cause. For example, one hypothesis is that a buildup of ketones, chemicals produced during certain metabolic processes, could make the body flammable. If a person's body has enough of these chemicals, coupled with a small spark, it might trigger an internal ignition. Another idea involves the wick effect, which is often mentioned when discussing these cases. In this scenario, a person's clothes could act like a wick, drawing fat from their body and allowing a small fire to burn intensely, while the surrounding area remains unaffected. But this doesn't explain why the fires seem to ignite without an obvious cause, or why they sometimes burn for hours. While there have been attempts to explain these events through science, the mystery remains. Why do some bodies combust while others don't, and why are these incidents so rare? Could there be some unknown physics at work? A hidden force or reaction that we don't yet understand? The case of spontaneous human combustion might not yet have a clear scientific explanation, but it continues to haunt us, reminding us that there are still many mysteries of the human body and the forces that govern it, waiting to be understood. Sun's corona temperature anomaly. When we think about the sun, we often picture its bright, blazing surface, the photosphere, glowing at around 5,500 degrees Celsius. But what's truly baffling is what happens just above that surface. The corona, the sun's outer atmosphere, which reaches a temperature of millions of degrees. This is a mystery that has left scientists scratching their heads for decades. How is it possible that the corona is so much hotter than the surface of the sun? This phenomenon is known as the corona temperature anomaly, and it's one of the most perplexing problems in solar physics. You'd expect the sun's outer atmosphere to be cooler than the surface, but instead, it's dramatically hotter. The current theory suggests that the sun's magnetic fields may play a role in heating the corona. These magnetic fields, which extend from the sun's surface, are incredibly powerful and could be carrying energy into the corona. But the exact mechanism by which this energy is transferred and how it causes such intense heat remains elusive. Some scientists speculate that Alf-Venn waves, ripples in the magnetic fields, could be transporting energy from the sun's interior to the corona. These waves, like a subtle cosmic ripple, might help to heat the corona in ways we don't yet fully understand. Others believe that magnetic reconnection, a process where magnetic fields suddenly snap and release energy, might be playing a role. Despite years of observation, the cause of the corona's extreme heat still defies explanation. What's even more intriguing is how this anomaly could have far-reaching consequences. Understanding how the sun's corona works could help scientists better predict solar storms, which can affect everything from satellite communication to power grids on Earth. Cosmological lithium problem. In the vast reaches of the universe, there's a problem that has puzzled scientists for decades: the cosmological lithium problem. It's a mystery hidden in the stars, and it raises an unsettling question. Where did all the lithium go? Lithium, a light element, was one of the first to form after the Big Bang. In the early universe, during a period known as Big Bang nucleosynthesis, conditions were just right for the creation of the first elements. Hydrogen, helium, and lithium were all produced in the hot, dense environment. However, astronomers and physicists have made an unexpected discovery. When they look at the amount of lithium in the universe today, there's far less than expected. According to the standard model of cosmology, the early universe should have produced more lithium than we observe now. The mystery is not that lithium is rare, but that there seems to be a significant discrepancy between the predicted and observed amounts, particularly in ancient stars and galaxies. So, what happened to this missing lithium? Some scientists suspect that stellar processes, like the fusion of elements in stars, might be destroying lithium over time. However, this doesn't explain the large gap in the amounts of lithium observed in the oldest stars, which formed early in the universe's history. Other theories suggest that perhaps our understanding of how the early universe worked is incomplete. Could there be unknown processes or factors at play that led to a smaller amount of lithium than expected? Or perhaps the solution lies in an overlooked aspect of astrophysics waiting to be discovered. The cosmological lithium problem challenges our understanding of the universe's earliest moments, urging scientists to reconsider what we think we know about the birth of elements. As we search for answers, one thing is clear: the universe still holds mysteries that even our most advanced theories can't fully explain. Titius-Bode Law Mystery. In the 18th century, a peculiar pattern was discovered in the distances between planets in our solar system, a pattern so uncanny that it seemed too perfect to be random. This pattern became known as the Titius-Bode Law, and for centuries it captivated scientists, offering an almost eerie glimpse into the organization of the universe. The law is surprisingly simple. It suggests that the distances between planets in our solar system follow a predictable mathematical sequence. Starting with Mercury, the planets seem to be spaced at roughly regular intervals when expressed in a specific mathematical formula. For example, the Earth is located 1 astronomical unit, AU, from the Sun, and the next planet, Mars, is about 1.5 AU away. The pattern continues, leading to an almost uncanny prediction of where the planets should be. But here's where the mystery begins. The Titius-Bode law works remarkably well for most of the planets. Mercury, Venus, Earth, Mars, Jupiter, and even Saturn. But there's one glaring exception: Uranus. According to the law, Uranus should be located at a certain distance from the Sun, but in reality, it's not. Even stranger, the law also predicted the existence of a planet between Mars and Jupiter, which was later discovered to be the asteroid belt. For a long time, the Titius-Bode law seemed almost too accurate to be coincidental. But the exception of Uranus, along with the fact that no new planets have been found in the predicted locations, has left scientists wondering: is this just a quirk of numbers, or is there something deeper behind this mysterious pattern? The Titius-Bode law raises more questions than answers. Could there be an unknown force or pattern at play in the solar system's formation? Something we're only beginning to understand. As we continue to explore the cosmos, the mystery of the Titius-Bode law remains unsolved, leaving us with the eerie feeling that the universe may be revealing its secrets in ways we can't fully comprehend. Fermi Bubbles. In the vast expanse of the Milky Way, a strange and eerie phenomenon stretches across the center of our galaxy. These mysterious structures, known as Fermi Bubbles, are enormous, glowing regions of high-energy gas, and they've baffled astronomers since their discovery in 2010. Fermi bubbles are giant, symmetrical bubbles of energy that extend about 25,000 light-years above and below the galactic plane. They were first spotted using data from NASA's Fermi Gamma Ray Space Telescope, which detects gamma rays, high-energy radiation. The bubbles shine brightly in gamma rays, but what's truly mysterious is what's causing them. They're so large and powerful that they suggest some enormous unknown event or series of events occurred at the heart of the Milky Way. One theory suggests that these bubbles are the result of energetic outflows from the supermassive black hole at the center of the galaxy. As matter falls into the black hole, it might send out powerful jets of energy, creating these massive bubbles of gas. But the timing and scale of such an event raise questions. How could such an eruption occur so far from the galactic center? And why have we never seen anything like this in other galaxies? Another theory proposes that the Fermi Bubbles could be the result of something even more mysterious: dark matter interactions. Some researchers believe that dark matter, an invisible substance that makes up most of the universe's mass, could be interacting in ways we don't fully understand, possibly contributing to the creation of these bubbles. The Fermi Bubbles continue to captivate scientists. Their eerie glow hints at something massive and unknown at the heart of our galaxy, and the mystery of their origin is still unsolved. Could they be signaling hidden forces at work, forces that could reshape our understanding of the universe itself? The answers remain elusive, leaving us with more questions than ever. Ghostly ring of dark matter. In the vast stretches of space, there are strange phenomena that continue to elude scientists, one of the most eerie being the ghostly ring of dark matter. It sounds like something out of a science fiction story, but it's a mystery that's rooted in real physics. Dark matter, an invisible substance that makes up about 85% of the universe's mass, doesn't emit light or energy, which is why we can't see it. We only know it exists because of its gravitational effects on visible matter. But scientists recently discovered something even more unsettling: an unusual ring-like structure that seems to be made of dark matter, and it's been found around galaxies. This ghostly ring doesn't behave like regular matter. It's almost as if the ring itself is something that's floating, separate from everything else, casting an invisible gravitational influence. The most surprising part is that these dark matter rings don't seem to match up with any known theory. They appear to be too large, too structured, and too strange to fit within the usual patterns we expect from galaxy formation. What's even more mysterious is that these rings don't have the typical characteristics of galaxy clusters or other known cosmic structures. Instead, they seem to hint at an unknown interaction of dark matter, possibly created during the earliest moments of the universe. Could this ghostly dark matter ring be the remnants of some ancient cosmic event? Or perhaps it's a clue to understanding dark matter's true nature. The discovery of these rings raises unsettling questions about how dark matter behaves on the largest scales. Could this strange, invisible force be far more organized and complex than we realize? The ghostly ring of dark matter remains an enigma, one that could potentially unlock new insights into the very fabric of the universe. Strange matter contagion hypothesis. Imagine a substance so strange, so powerful, that if it were to touch normal matter, it could transform everything it came into contact with, turning the world around us into a completely different kind of material. This is the chilling idea behind the strange matter contagion hypothesis, and it might just be one of the most unsettling concepts in modern physics. Strange matter is a theoretical form of matter that is made up of strange quarks, particles that are normally found only in the extreme conditions inside a neutron star or created during high-energy particle collisions. Unlike regular matter, which is made up of protons, neutrons, and electrons, strange matter is thought to be much more stable under extreme pressures, potentially forming a material that's far denser and more stable than anything we encounter on Earth. Now, the mystery lies in the contagion hypothesis. This theory suggests that if strange matter were somehow created or encountered outside of these extreme conditions, perhaps in a laboratory or through a high-energy collision, it could spread like a wildfire, turning ordinary matter into strange matter. Once the process starts, it could, in theory, continue indefinitely. consuming everything it touches, eventually transforming the entire planet, or even the entire universe, into this new form of matter. The idea is eerily similar to a chain reaction of sorts, but one where normal matter is replaced by a completely alien substance. The scary part: we don't know if strange matter is real, let alone if it could actually spread, but the possibility of its existence and the potential for something so uncontrollable and dangerous raises important questions about the safety of high-energy experiments and the stability of the universe itself. The strange matter. Contagion. Hypothesis isn't just a scientific curiosity. It's a reminder that there are still many mysteries in the universe that could change everything we think we know about matter, energy, and the laws of physics. The search for answers continues, but the threat of strange matter remains an eerie possibility, lurking at the edges of our understanding. Vacuum catastrophe. Imagine the universe as a vast, empty space, filled with an energy field known as the vacuum, the so-called nothingness of space. But what if this vacuum isn't as empty as we thought? What if it's teetering on the edge of a cataclysmic shift, one that could change everything? This is the mystery of the vacuum catastrophe. In physics, the vacuum is not truly empty. It's filled with a type of energy called vacuum energy, which comes from the fluctuations of quantum fields. These fluctuations can give rise to tiny particles that pop in and out of existence. However, there's a problem. When scientists try to calculate how much energy should exist in the vacuum, they come up with a number that is trillions of times greater than what we actually observe in the universe. This discrepancy is known as the vacuum catastrophe. The mystery deepens when we consider the implications of this vast difference in energy. Theoretically, if the vacuum energy were as high as predicted, it would cause the universe to collapse in on itself, essentially leading to the end of everything. The fact that this hasn't happened is puzzling. How does the universe manage to avoid this catastrophic fate? Some physicists believe that the vacuum might be in a metastable state, like a ball sitting at the top of a hill, ready to roll into a new, lower energy state. If this happens, it could trigger a chain reaction that would alter the very structure of space-time, destroying everything as we know it. But for now, this ticking time bomb remains stable. The vacuum catastrophe forces us to question the stability of the universe itself. How much do we really understand about the fabric of reality? And could the very nature of nothingness hold the key to the universe's most profound secrets? The answers remain elusive, leaving us to wonder just how fragile our reality might be. Zero-point energy exploitation. Imagine tapping into an energy source that's all around us, yet invisible. An endless, untapped reservoir of power that could fuel the future of civilization. This is the promise of zero-point energy, a mysterious phenomenon lurking at the quantum level of the universe. But while scientists have speculated about its potential for decades, the question remains: can we actually exploit it? Zero-point energy is the energy present in a vacuum, even when it seems empty. In quantum mechanics, particles are constantly fluctuating, popping in and out of existence, even in a perfect vacuum. These fluctuations mean that space is never truly empty. It's filled with this subtle quantum energy. In theory, this energy is limitless, existing throughout the entire universe. The mystery lies in whether we can access and harness this energy for practical use. If we could tap into zero-point energy, it might provide an unlimited, clean power source. Imagine a world without energy scarcity, where power is drawn directly from the vacuum itself. But there's a problem. While zero-point energy is theoretically real, no one has figured out how to access it, or if it's even possible to do so. Scientists and inventors have speculated about devices that could extract this energy, but so far, none have succeeded. Some researchers believe that the key might lie in understanding the fundamental physics that govern quantum fields and space-time. Could there be a way to manipulate these fields, bending them to release the hidden energy? The mystery of zero-point energy exploitation challenges our understanding of physics and could unlock a new era of technological advancement. But until we find a way to tap into this mysterious force, the potential of zero-point energy remains just out of reach, teasing us with the possibility of an energy revolution waiting to be discovered. Anti-gravity effects in superconductors. In the world of physics, few things are as fascinating or as mysterious as the potential for anti-gravity. Imagine a material that, under the right conditions, could defy gravity, floating above the ground as if suspended by an invisible force. This is the eerie possibility suggested by anti-gravity effects in superconductors. Superconductors are materials that, when cooled to extremely low temperatures, lose all electrical resistance, allowing electricity to flow without any energy loss. But beyond their ability to conduct electricity perfectly, superconductors have a strange, almost magical property. They can repel magnetic fields. This is known as the Meissner effect, and it's a crucial part of how anti-gravity effects might work. The Meissner effect essentially causes a superconductor to expel magnetic fields from its interior, leading to the floating or levitating effect. When placed in a magnetic field, a superconductor can push back, creating the illusion of anti-gravity. But here's the mystery. While scientists have observed this levitation for decades, the mechanisms behind it remain elusive. Why do superconductors behave this way? And could this levitation effect be harnessed for practical use, like transportation or advanced technology? Some researchers are even speculating that these anti-gravity effects could be used to create gravitational shielding, a technology that could one day reduce or even eliminate the effects of gravity altogether. But even with all the advances in superconductor research, no one has yet fully understood how these materials interact with gravity in such a way that allows them to defy it. The mystery of anti-gravity in superconductors teases at the possibility of a future where we can manipulate gravity, opening up a world of possibilities from levitating vehicles to advanced propulsion systems. But for now, the exact nature of this strange phenomenon remains one of the greatest unsolved mysteries in physics. Could this be the first step toward a new frontier of technology? Or is the true nature of anti-gravity still just beyond our grasp? Cold fusion phenomenon. In 1989, two electrochemists, Stanley Pons and Martin Fleischmann, made an announcement that sent shockwaves through the scientific community. They had achieved cold fusion, a process where nuclear fusion, the same reaction that powers the sun, occurs at room temperature. If true, cold fusion could revolutionize the world, providing an endless, clean source of energy. But decades later, the mystery remains unresolved, with cold fusion still teetering between hopeful breakthrough and controversial enigma. Cold fusion is supposed to happen when two hydrogen nuclei fuse together to form helium, releasing vast amounts of energy in the process. This is the same process that powers stars, but normally, fusion requires incredibly high temperatures and pressures, millions of degrees. Pons and Fleischmann's claim suggested that fusion could occur under much milder conditions, something unheard of in the world of nuclear physics. But here's the catch. Despite the excitement, other scientists struggled to replicate their results. Many attempts to verify cold fusion failed, leading to widespread skepticism. The mainstream scientific community largely dismissed it as a mistake or misinterpretation. Yet some researchers still pursue the idea, with occasional reports of unusual energy readings and unexplained results. The mystery deepens when we consider what cold fusion could mean. If it were possible, it would provide an energy source that is cheap, abundant, and non-polluting. Essentially, a perfect solution to the world's energy crisis. However, the lack of consensus and inability to reliably replicate the results raises questions. Is cold fusion real, or is it simply a scientific myth waiting to be debunked? The cold fusion phenomenon lingers on, a tantalizing possibility that could rewrite the rules of energy production, if only we could fully understand it. The mystery persists, inviting scientists to keep searching for answers in the uncharted depths of physics. Sonoluminescence Paradox. In a laboratory, something strange happens when sound waves are turned up to extreme levels. Tiny bubbles, no bigger than a speck of dust, suddenly emit bursts of light. This phenomenon, known as sonoluminescence, has puzzled scientists since it was first discovered decades ago. How can a simple bubble, pulsating under the influence of sound, create such intense light? Here's the mystery. When sound waves hit a gas bubble submerged in a liquid, they cause the bubble to rapidly collapse and compress. During this collapse, the bubble emits a brief flash of light, almost as if it were a tiny star flickering in a dark room. This is the paradox. How does a bubble, with no visible energy source, generate light so intense? Some estimates say that inside the collapsing bubble, temperatures reach thousands of degrees, hotter than the surface of the sun, but the bubble itself is too small to have any conventional energy source like electricity or heat to explain this. The paradox deepens when you consider that all the laws of energy conservation seem to be defied. Normally, light comes from energy sources like chemical reactions or electrical currents. But in sonoluminescence, the bubble appears to spontaneously turn sound energy into light. It raises the question, how does sound, a form of pressure, convert into light and heat without breaking the laws of physics? Despite decades of research, the exact mechanism remains unclear. Some scientists suspect quantum mechanics might play a role, while others propose that it's the complex dynamics of the bubble itself. Sonoluminescence is more than just a curious lab experiment. It's a mystery that challenges our understanding of energy, sound, and light, leaving us to wonder, what secrets does the universe hold in the tiniest of bubbles? The search for answers continues, and the mystery remains as intriguing as ever. Emission of X-rays from comets. Imagine a comet, one of the oldest and most mysterious objects in our solar system, traveling through the void of space, its tail trailing behind it like a dusty ribbon. We've long known that comets are made of ice, dust, and gases. But here's the mystery. Scientists have discovered that at times, comets emit X-rays, high-energy radiation that we normally associate with things like the sun or black holes, not icy bodies from the outer reaches of space. This strange phenomenon was first observed in the 1990s, when scientists detected unexpected X-ray emissions coming from comet Hyakutake and later from comet Hale-Bopp. These comets, like all comets, contain icy material that evaporates as they approach the sun, creating the bright tails we see. But no one expected that these relatively small, icy bodies would emit X-rays. So, where are these X-rays coming from? The mystery deepens when we consider the source of such high-energy radiation. One theory is that these X-rays are being produced when solar wind, charged particles from the sun, interacts with the gases around the comet. The particles might be colliding with the comet's coma, the cloud of gas and dust surrounding it, causing it to emit X-rays. But this doesn't fully explain why the X-ray emissions seem to vary, sometimes being stronger or weaker depending on the comet's location relative to the Sun. Could there be something more to these mysterious emissions? Perhaps an unknown interaction or force that we don't yet understand? The mystery of X-ray emissions from comets is a reminder of how much we still don't know about the cosmos. These ancient visitors from the outer solar system continue to surprise us, revealing secrets that challenge our understanding of both comets and the forces that shape our universe. Long-delayed echoes of radio signals. Imagine you're listening to a radio signal, but instead of hearing it just once, you hear it again and again, delayed by several seconds. It's as if the signal is bouncing off something far away, only to return to you long after the original transmission. This is the mystery of long-delayed echoes of radio signals, an eerie phenomenon that has baffled scientists for decades. It all started in the 1920s, when radio operators first noticed that signals sent from Earth didn't always travel straight through the atmosphere. Instead, they sometimes bounced back after a long delay. The echoes, which could last from seconds to even minutes, were unlike any normal reflection of radio waves. They weren't caused by buildings or mountains, as you might expect. They came from far off in the atmosphere or beyond. One theory suggests that these mysterious echoes could be the result of ionized layers in Earth's upper atmosphere, particularly the ionosphere, which reflects certain radio frequencies. When these layers are disturbed, they could cause radio waves to reflect and return much later than expected. But this explanation doesn't fully account for the more unusual and longer than expected delays, which seem to defy simple explanations. Some scientists have even speculated that the long-delayed echoes could be caused by more unusual interactions in the atmosphere, or even unknown atmospheric conditions that we don't fully understand yet. Could the Earth's atmosphere be behaving in ways we've never considered, creating reflections from mysterious regions of space? While the exact cause of these delayed echoes remains unclear, the phenomenon continues to puzzle researchers. It raises the eerie possibility that there are hidden forces or unseen structures in our atmosphere that we're just beginning to uncover. The mystery of long-delayed echoes leaves us with more questions than answers, hinting at a deeper, unknown layer of reality just beneath our feet. Fast radio burst patterns. In the vastness of space, there's a signal that's both mysterious and haunting. Fast radio bursts, or FRBS. These high-energy bursts of radio waves last just a few milliseconds, yet in that brief moment, they release more energy than our entire sun emits in a day. But the real mystery? We still don't know what causes them, and more strangely, there's an intriguing pattern to their occurrence. First discovered in 2007, FRBs have left scientists baffled. These bursts appear to come from far beyond our galaxy, but their exact origin is unknown. What makes them so strange is that they are incredibly brief, lasting only a fraction of a second. Yet the energy they release is mind-boggling. It's as if someone is sending out a cosmic flash. But from where? And why? The mystery deepens when you look at the patterns in the bursts. Some FRBs seem to follow a regular schedule, coming in bursts or repeating at predictable intervals. Others appear to travel through space in ways that suggest there might be an unknown structure or force causing them. This repetitive nature hints that FRBs aren't random, but could be tied to specific cosmic events, possibly involving magnetic fields or exotic objects like neutron stars or black holes. Some scientists have even proposed that FRBs could be signals from alien civilizations, though this remains purely speculative. The more likely explanation involves extreme astrophysical events, but the precise cause remains one of the most captivating mysteries in modern physics. Every new FRB discovered deepens the enigma, urging researchers to rethink our understanding of space and energy. Are we witnessing the echoes of a distant event in the universe, or is there a hidden force we've yet to uncover? The answer remains elusive, but the hunt for it continues, pulling us deeper into the unknown. Neutron star glitches. Deep in the heart of space, there are objects so dense, so mysterious, that their very existence challenges the limits of our understanding. Neutron stars, the remnants of massive stars that have exploded in supernova, are among the strangest and most fascinating objects in the universe. These stars are incredibly compact, packing more mass into a sphere just a few kilometers across than the Sun contains in its entirety. But here's the mystery. Every now and then, neutron stars exhibit strange, sudden glitches in their behavior that scientists can't fully explain. Neutron stars spin rapidly, up to several hundred times per second, and they emit beams of radiation, which we observe as pulsars. These regular pulses of energy should follow a predictable rhythm, but occasionally something strange happens. These pulses suddenly become erratic, as if the neutron star has glitched. The glitch can be small, causing a temporary shift in the timing of the pulses, or it can be more dramatic, leading to a complete break in the pattern. The mystery lies in understanding what causes these glitches. Some researchers believe the cause could be interior changes inside the neutron star, like sudden shifts in its dense, superheated core. Others think that the glitches could be related to the magnetic fields of the star or the way the star's crust behaves under extreme pressure. But the most unsettling theory is that the glitches could be linked to something even more unknown, perhaps quantum effects or new physics that we don't yet understand. Could the glitches be signaling that neutron stars are behaving in ways that challenge everything we know about matter, energy, and space-time? The phenomenon of neutron star glitches continues to baffle scientists, offering us a tantalizing glimpse into the strange, hidden forces at play in the most extreme environments in the universe. And with each new glitch, the mystery deepens, pulling us closer to uncovering the secrets of these cosmic anomalies. Strange pulsar signals. In the depths of space, there are stars that behave in the most extraordinary ways. Pulsars, which are rapidly spinning neutron stars, send out regular pulses of energy, like cosmic beacons flashing across the galaxy. These signals are typically predictable, a steady rhythm that scientists have come to understand over decades of observation. But every so often, something strange happens. Pulsar signals that defy explanation. The mystery of these strange pulsar signals started with an unusual discovery in 2018. Researchers observed a pulsar emitting irregular, seemingly random bursts of energy, unlike any previously detected. Normally, pulsars produce steady signals, like a lighthouse beacon, timed precisely with the star's rotation. But this pulsar was different. Its signals were inconsistent, with gaps, bursts, and changes in frequency that suggested something was disrupting the star's usual pattern. What could cause this? Scientists began to speculate that the pulsar might be influenced by something in its environment, perhaps an interaction with a nearby object like a companion star, or even the magnetic fields within the pulsar itself. Another theory points to the idea that something within the pulsar's own structure, like the way its crust behaves under extreme pressure, could be altering the emission patterns. But here's where the mystery deepens. Could these strange signals point to something even more elusive, such as the existence of unknown cosmic phenomena or exotic physics, Some have even wondered if the irregular signals could be a result of dark matter or interactions between quantum fields in ways we've never observed before. These strange pulsar signals continue to baffle astronomers. With every new anomaly, we inch closer to unraveling the hidden forces shaping these mysterious stars. The question remains, what is truly behind these unexpected, eerie signals? And could they be pointing us toward a deeper, undiscovered layer of the universe? Ultra-high energy neutrinos. Deep in the universe, there are particles that pass through everything, our planet, our bodies, without leaving a trace. These particles are called neutrinos, and they are some of the most elusive in the universe. But there's a particular type of neutrino that has scientists both fascinated and perplexed. Ultra-high energy neutrinos, UHE neutrinos. These neutrinos are incredibly rare, and they carry energy levels so high that they're far beyond what we typically encounter in cosmic radiation. They come from deep space, and when detected on Earth, they provide a rare glimpse into the most energetic and mysterious events happening in the universe. The catch? We don't know where they're coming from. UHE neutrinos have been observed by detectors like the Ice Cube Neutrino Observatory at the South Pole, which uses miles of sensors buried in the Antarctic ice. When these high-energy neutrinos interact with the ice, they create faint signals that can be traced back to their origins. But the real mystery lies in the source. Scientists have a few theories. These neutrinos could be coming from supermassive black holes at the centers of distant galaxies or gamma-ray bursts, the most powerful explosions in the universe. But we haven't pinpointed exactly where or how these particles are being generated. What makes these neutrinos so intriguing is that they defy our understanding of physics. Why are these particles so energetic? And how do they manage to travel across the vast expanse of space without losing their energy? Some even speculate that ultra-high energy neutrinos could be tied to dark matter or unknown cosmic phenomena, forces we haven't yet discovered. The mystery of UHE neutrinos challenges the limits of our knowledge, pushing us to explore the farthest reaches of space and the fundamental forces of nature. The answers could reveal an entirely new chapter in our understanding of the universe itself. GZK limit cosmic rays. In the vastness of space, high-energy particles known as cosmic rays zip through the universe, traveling at nearly the speed of light. These particles are some of the most energetic things we know, yet they come from places so distant, it's almost as if they're reaching us from another time. But here's the mystery. Some of the most powerful cosmic rays seem to violate a fundamental rule of physics. They shouldn't be able to reach us at all. This strange phenomenon is known as the GZK limit. Named after the scientists who first proposed it, the GZK limit predicts that cosmic rays, specifically the highest energy ones, shouldn't be able to travel more than about 100 million light-years before losing their energy. The reason is simple. Cosmic rays are constantly colliding with particles in the cosmic microwave background, a faint glow left over from the Big Bang. These collisions should cause the cosmic rays to lose energy, preventing them from reaching Earth. Yet, despite this prediction, astronomers have observed ultra-high energy cosmic rays arriving at Earth from distant galaxies, beyond the expected GZK limit. These particles carry far more energy than they should be able to maintain over such vast distances. The mystery is clear. How are these cosmic rays making it here? Some scientists speculate that these rays could be traveling from nearby active galaxies or supermassive black holes, while others suggest that there could be unknown forces at play, perhaps even hinting at the existence of exotic particles or dark matter. Could these particles be the key to unlocking new insights into the structure of the universe? The GZK limit mystery challenges our understanding of the cosmos, pushing us to consider that the universe might be far stranger than we think. These cosmic rays, traveling through the fabric of space-time, may hold secrets that could change the way we understand the universe itself. The search for answers continues, and the mystery deepens. Hyperspace jump theories. Imagine being able to travel across the vast distances of space in the blink of an eye. What if there was a way to jump from one point in the universe to another without the long, slow journey through space? This is the concept of hyperspace jumps, and while it sounds like something straight out of science fiction, it's a mystery that has intrigued physicists for decades. The idea of hyperspace travel comes from the theory that in certain conditions, the fabric of space-time could be manipulated in such a way that it allows for faster-than-light travel. Instead of moving through space as we know it, a spacecraft could enter a higher dimensional space, a kind of shortcut through the universe that bypasses the long distances between objects. One of the most famous ideas for hyperspace jumps comes from wormholes, theoretical passages through space-time that could connect distant parts of the universe. Picture them as tunnels in the fabric of space, where one end could be near Earth and the other near a distant galaxy. If wormholes exist, they could potentially allow for rapid travel between far-off places. But here's the problem. We've never observed a wormhole. And even if one did exist, scientists still don't know how to keep it open or stable enough for travel. Another theory involves manipulating space-time itself using advanced technology, like warp drives. A warp drive could, in theory, bend space in front of a spacecraft, creating a bubble that moves faster than light, without actually violating the laws of physics. But again, this idea faces enormous challenges, as the energy requirements for such a feat would be mind-boggling. The mystery of hyperspace travel raises deeper questions about the very nature of space and time. Could there be hidden dimensions or forces at play that we haven't yet discovered? The concept of hyperspace travel challenges our understanding of the universe, leaving us with a tantalizing question. Is the key to faster-than-light travel already within the fabric of reality, waiting for us to unlock it? Simulation hypothesis backed by physics. What if everything you see, hear, and experience is nothing more than a sophisticated simulation, like a video game, but so advanced that it feels completely real? This eerie possibility is the core of the simulation hypothesis, an idea that's moved beyond science fiction and into the realm of serious scientific debate, backed by some surprising concepts in physics. The idea is simple. Perhaps our reality, the universe itself, is actually a simulation created by a far more advanced civilization. It's like how we simulate worlds in video games, but on a cosmic scale. But what's even more intriguing is that some scientists think physics might actually support this theory. One of the key points is the nature of quantum mechanics, where particles behave in ways that don't always make sense. For example, particles can exist in multiple states at once until observed, and the act of measuring can influence their behavior. Some argue that these strange behaviors could be evidence of the underlying code or rules governing a simulated reality. After all, in a computer simulation, things only exist when they are observed or interacted with. Could this explain the peculiarities of quantum physics? Another interesting aspect comes from the limits of computing power. As technology advances, humans are creating more sophisticated simulations, with virtual worlds that feel incredibly real. Some theorists argue that if future civilizations continue to develop, they might have the computational power to simulate entire universes. If they can do it, why couldn't we be in one? While no definitive evidence exists, The idea that our reality could be a simulation challenges our very understanding of existence itself. The possibility that the universe is a construct, one that might be manipulated or programmed, forces us to confront a question that is as old as philosophy itself. What is the true nature of reality? And if we are living in a simulation, what lies beyond the boundaries of our perceived world? Retrocausality. Imagine a world where the future can influence the past, where effects occur before their causes. It sounds like something out of science fiction, but this is exactly the concept of retrocausality, a theory that has been quietly intriguing physicists and philosophers for years. In the world of quantum mechanics, time often behaves in ways that defy our everyday understanding. In typical life, we're used to causes leading to effects in a clear, logical order. Something happens, and that causes something else to happen afterward. But at the quantum level, particles seem to behave differently. They can exist in multiple states at once, and what happens next can sometimes depend on how we look at them. Here's where retrocausality comes in. What if the behavior of particles in the present is influenced by future events? What if, in some circumstances, the future causes something to happen in the past? This could turn the whole concept of time on its head. Some theories suggest that retrocausality could explain strange phenomena like quantum entanglement, where two particles can instantaneously affect each other no matter the distance between them. Normally, we think that events unfold in one direction, from past to present to future. But retrocausality hints that the future could, in some mysterious way, reach back and alter events that have already happened. The implications of retrocausality are mind-boggling. Could time travel be possible, not in the way we've traditionally imagined, but through future events influencing the past? And if retrocausality is true, does it suggest that time itself might not be as linear and fixed as we think? For now, the mystery of retrocausality remains unsolved. But every new discovery in quantum physics brings us one step closer to answering this unsettling question. Is time really just a one-way street? Or could it be far more fluid than we ever imagined? Closed, time-like curves. Time travel has long been a subject of fascination and mystery. But what if time itself was more flexible than we ever imagined? What if there were paths in the fabric of space-time that could loop back on themselves, allowing you to travel into your own past? This eerie concept is known as closed time-like curves, CTCs, and it could unlock a mystery that challenges everything we think we know about time and causality. In Einstein's theory of general relativity, space and time are intricately connected. They form a fabric that can be curved and shaped by gravity. Under certain extreme conditions, like those near a black hole or in a rotating massive object, this fabric could, in theory, bend in such a way that time itself forms a closed loop. Picture it like drawing a circle in space. You start at one point and eventually find yourself back where you started. But this happens in time, not just space. What makes closed time-like curves so strange is that they allow for the possibility of traveling back in time, effectively creating a time loop. Imagine going back in time to a point where you made a decision, but now with the ability to alter it. Could such loops be the key to time travel, or do they open up paradoxes that we can't yet understand? The mystery deepens when we consider the potential consequences of CTCs. Could they allow for grandfather paradoxes, where travelling back in time prevents your own existence? Or could they provide a bridge to other dimensions or timelines we've never considered? While closed, time-like curves are still purely theoretical, Their eerie implications make them one of the most captivating mysteries in physics. What if time is not the straight line we think it is, but a loop with the power to twist, turn, and perhaps even break? The search for answers continues, and the possibilities are as mysterious as time itself. Tachyons, faster-than-light particles. Imagine a particle that can travel faster than the speed of light, a feat that defies everything we know about the universe. This is the strange and mysterious world of tachyons, particles that, if they exist, could shatter our understanding of physics. In Einstein's theory of special relativity, nothing can exceed the speed of light. It's a fundamental rule that has stood the test of time. But tachyons are theoretical particles that break this rule. According to some physicists, these particles would have imaginary mass, meaning they could travel faster than light, but they would behave in ways that seem completely unnatural in our current understanding of physics. The mystery starts with the fact that tachyons have never been observed. No one has seen a tachyon in action, but they appear in certain equations in theoretical physics. Some scientists believe that if tachyons exist, they could explain a number of bizarre phenomena. For example, could they be connected to dark matter, the unseen substance that makes up most of the universe's mass? Or might tachyons somehow be linked to the mysteries of quantum mechanics or the behavior of space-time itself? Another unsettling possibility is that tachyons could offer a glimpse into time travel. If they can move faster than light, could they also travel backward in time, creating strange paradoxes or allowing for the possibility of altering past events? Despite the lack of direct evidence, tachyons remain an intriguing possibility in theoretical physics. Could they exist in some hidden corner of the universe, waiting to be discovered? Or are they simply a mathematical curiosity, a puzzle that might never be solved? The mystery of tachyons continues to captivate scientists, leaving us to wonder if the laws of physics are more flexible than we've ever imagined. Pioneer Plaque Misinterpretation Hypothesis. In 1972, a message was sent out into the vastness of space, a bold attempt to reach any intelligent life beyond Earth. The Pioneer Plaque, attached to the Pioneer 10 spacecraft, depicted a human figure, an outline of our solar system, and a message intended to communicate our existence to extraterrestrial beings. But what if this well-intended message was actually misinterpreted, leading to an unintended and eerie mystery? The plaque's design was carefully crafted by scientists Frank Drake and Carl Sagan to be universal, using simple pictorial symbols. But what if these symbols, which were meant to be understood across the vast void of space, could be interpreted in completely different ways by an alien civilization? Could the symbols on the Pioneer plaque, rather than being a universal message, become a cryptic puzzle? This is the Pioneer Plaque Misinterpretation Hypothesis. One of the biggest challenges is that we're assuming the aliens would think like us. But different civilizations, whether in distant galaxies or even on Earth thousands of years ago, could have vastly different ways of interpreting images or symbols. For instance, the depiction of a human figure on the plaque assumes that extraterrestrial beings would recognize and understand human form, but they might see something entirely different. Could they interpret the human figure as a form of hostile intent or an invitation for contact, triggering unpredictable consequences? Moreover, the plaque's instructions on Earth's location within the solar system might be confusing or unclear. The message might assume knowledge of certain astronomical concepts that other civilizations might not understand at all. This hypothesis leaves us with an unsettling possibility. The Pioneer plaque, rather than a hopeful bridge to the stars, could be an enigmatic message that creates more questions than answers. Could the search for alien life lead to unexpected misunderstandings? The Pioneer plaque still traveling through space, may carry more than just our message. It might also hold a reminder that communication across vast distances is fraught with uncertainty. Non-quantized redshift. In the vast stretches of the universe, light travels across unimaginable distances, carrying with it vital information about the stars and galaxies it passes. One of the key tools scientists use to understand the cosmos is redshift, a phenomenon where light from distant objects appears stretched or shifted towards the red end of the spectrum. This happens when objects move away from us, and it's usually a key indicator that the universe is expanding. But recently, a strange mystery has emerged, one that challenges everything we thought we knew about redshift. Non-quantized redshift. Normally, the redshift observed in light from distant galaxies is predictable and smooth. The farther away a galaxy is, the greater the redshift. However, scientists have started to notice something strange. Some galaxies appear to have redshifts that don't follow the expected pattern. Instead of a smooth, continuous change, these galaxies exhibit discrete jumps in their redshift values, as though they're jumping from one quantum level to another. This is what we call non-quantized redshift. So, what does this mean? Redshift is usually considered a simple consequence of the expanding universe, light stretched as it travels across space. But if redshift isn't quantized, it implies there could be something else at work. Perhaps a new force, or a hidden pattern in the universe's structure that we haven't yet uncovered. Some theorists even speculate that these jumps in redshift could be evidence of cosmic scale phenomena, such as interactions between galaxies, or even the influence of dark matter. The mystery of non-quantized redshift challenges our understanding of the universe's expansion. If redshift is behaving in ways we don't expect, it could suggest deeper, more fundamental layers to the nature of space-time itself. Could we be on the verge of discovering something profound, something that redefines our place in the cosmos? The search for answers continues, and with it, the possibility of unraveling new mysteries hidden in the very fabric of the universe. UV catastrophe. At the turn of the 20th century, physics was on the brink of a major revolution. But in 1900, a perplexing problem nearly brought the entire field to a halt. This mystery is known as the ultraviolet catastrophe, and it has baffled scientists ever since its discovery. The story begins with a scientist named Max Planck, who was trying to understand how objects emit light. At the time, scientists believed that they could calculate the intensity of radiation emitted by objects based on their temperature. But when they applied the formulas, something strange happened. At shorter wavelengths, like ultraviolet light, the calculations predicted an infinite amount of energy, which clearly couldn't be possible. This was the catastrophe. The theory was broken, and it seemed like the laws of physics were about to collapse. According to the classical physics of the day, as the wavelength of light shortened, the intensity should increase without limit. But we don't see infinite energy radiating from everyday objects. Instead, objects like the sun emit light in a more measured way. So, why was classical physics failing? The mystery was solved by Planck himself. He proposed a groundbreaking idea. Energy is emitted in discrete chunks, what we now call quanta. This idea went against everything physics had believed before. Planck's theory, though initially hard to accept, marked the birth of quantum mechanics, the science that would ultimately change our understanding of the universe. The ultraviolet catastrophe revealed a deep flaw in classical physics, pushing scientists to develop new theories. It was a pivotal moment that sparked the quantum revolution, leading to discoveries that reshaped everything we know about energy, light, and matter. What began as a mystery in the realm of ultraviolet light ultimately led to the exploration of the very foundations of the universe itself. The ultraviolet catastrophe didn't just solve a problem, it opened the door to an entirely new chapter in physics. N-rays controversy. In 1903, a scientist named René Blondlot claimed to have discovered a new form of radiation. He called it N-rays, and he believed it was a type of invisible light emitted by all matter. Blondlot's findings were met with excitement. Here was a potential breakthrough in physics that could explain unknown phenomena. But as quickly as N-rays captured the scientific world's attention, they became embroiled in one of the most baffling and mysterious controversies in scientific history. Blondlot and his team had observed that certain materials, like metals and crystals, seemed to emit these N-rays under specific conditions. He even devised experiments to detect them, claiming to have seen effects like changes in the brightness of light bulbs, or shifts in the properties of materials when exposed to N-rays. But here's where the mystery begins. When other scientists attempted to replicate Blondlot's results, something unsettling happened. They couldn't. Even when they followed his methods to the letter, N-rays remained elusive. What was going on? Could this be a breakthrough, or was something else at play? The controversy took a strange turn when an American physicist, John Abrahamson, attended a demonstration by Blondlot. He secretly removed a key part of the experimental setup, a prism intended to detect N-rays. When Blondlot continued to report seeing the same effects, even without the prism, it cast serious doubt on the existence of N-rays. Eventually, Blondlot admitted that his results might have been influenced by the placebo effect, or his own expectations. The N-ray mystery raises an unsettling question. How can scientific discovery be so easily clouded by belief and expectation? The controversy of N-rays remains a cautionary tale, reminding us of the importance of skepticism, verification, and the dangers of confirmation bias in the pursuit of knowledge. The impossible EM drive. Imagine a spacecraft that could travel across the stars without the need for traditional fuel. No massive engines, no giant fuel tanks, just a small, mysterious device generating thrust out of nowhere. This is the promise of the EM drive, an invention that, on the surface, seems like something out of science fiction. But in 2001, a British engineer named Roger Scheuer introduced the world to the EM drive, a device that, if it works, could revolutionize space travel as we know it. The mystery of the EM drive lies in its ability to produce thrust without expelling any propellant. Traditional propulsion systems, like rockets, work by pushing against the expelled gases or particles. But the EM drive appears to break this fundamental rule of physics. The device generates thrust using microwave radiation, which is contained within a cavity. Despite no conventional fuel being involved, the EM drive seems to push forward, as though violating the law of conservation of momentum. At first, scientists were skeptical. Some suggested that the observed thrust was just an experimental error or interference from external factors. But in 2014, a team of researchers at NASA's EagleWorks laboratory conducted their own tests. To their surprise, they detected a small but measurable amount of thrust coming from the device, confirmation that something extraordinary might be happening. Yet, even with the evidence, the mystery remains unsolved. How could the EM drive generate thrust without breaking the laws of physics? Could it be exploiting some unknown principle of quantum mechanics or space-time itself? The EM drive continues to defy explanation, leaving scientists both excited and cautious. If it truly works, it could take us beyond our solar system. But until the physics behind the device is fully understood, the EM drive remains one of the most perplexing mysteries in modern physics, a potential breakthrough just waiting to be unlocked. Woodward Effect. In the world of theoretical physics, there are ideas that could change everything we know about how things move and interact. One such mystery is the Woodward Effect, a phenomenon that, if proven true, could revolutionize space travel. It all began with physicist James Woodward, who proposed a strange idea: that certain objects could experience a force, a push, without any conventional means of propulsion. No exhaust, no fuel, just pure thrust. This force, now called the Woodward Effect, might seem impossible at first. It suggests that through the careful manipulation of energy and mass, objects could generate thrust, like a rocket, but without the need for any exhaust gases or physical propellants. The theory behind the Woodward Effect is based on a concept called mass fluctuations. Woodward speculated that by using certain types of electromagnetic fields, it might be possible to influence these fluctuations in an object's mass, causing it to accelerate. Essentially, the object would be pushed forward without any conventional means of propulsion, simply by manipulating the forces around it. The mystery begins with the fact that the Woodward Effect has been difficult to prove. Some experiments show small amounts of force, but the results are often inconclusive or controversial. Does this effect really work? Or is it an experimental artifact, an illusion caused by unseen variables? What makes the Woodward Effect particularly intriguing is its potential implications. If this phenomenon is real, it could allow us to propel spacecraft without the need for massive fuel or traditional propulsion systems, paving the way for interstellar travel. For now, the Woodward Effect remains an unsolved mystery, one that could open the door to a new era of space exploration, or perhaps lead us down a path of scientific curiosity that challenges everything we know about the fundamental laws of physics. The search for answers continues, but the potential is both thrilling and mysterious. Klein-Gordon negative probability. In the world of quantum physics, there are many strange phenomena that challenge our understanding of reality, but one of the most mind-boggling is the concept of negative probability, and it's tied to a fundamental equation known as the Klein-Gordon equation. The Klein-Gordon equation is a mathematical description of particles, particularly those that travel close to the speed of light, like bosons. It's a cornerstone of quantum field theory, which describes how particles interact with each other. But when scientists began studying the equation more closely, they made a baffling discovery. It sometimes produces negative values for probability, something that shouldn't be possible. In classical physics, probability is always positive. It's the chance that something happens, whether it's rolling a die or predicting the weather. But in quantum mechanics, probabilities are more complex. When the Klein-Gordon equation is applied to certain systems, it can give you a negative probability, which raises an unsettling question. Can negative probabilities even exist? On the surface, this seems impossible. How can the likelihood of something happening be negative? The answer isn't entirely clear. Some physicists believe that negative probabilities could be a sign of unexplored physics, hinting at deeper, unknown forces in nature. Others suggest that it's simply an artifact of the equation itself, an issue with how we're interpreting the math rather than a physical reality. What makes the Klein-Gordon negative probability mystery so intriguing is its implications. Could this strange anomaly be a clue to a hidden layer of the universe? A deeper understanding of negative probabilities could reveal new dimensions of physics, ones we don't yet fully grasp. The mystery remains unsolved, but the possibility of negative probabilities opens up a world of new questions leaving us to wonder just how much of our reality is waiting to be uncovered. The search for answers continues, and with it, the possibility of rewriting the laws of physics as we know them. Causality violations in quantum mechanics. In the realm of quantum mechanics, reality behaves in strange, often counterintuitive ways. One of the most puzzling aspects of quantum physics is its tendency to violate causality, the principle that cause always precedes effect. This mystery, causality violations in quantum mechanics, challenges everything we thought we knew about time and space. Causality is a cornerstone of classical physics. It's what we experience in everyday life. You turn on a light switch and the light comes on. Cause and effect are straightforward and predictable. But quantum mechanics, the theory that governs the behavior of subatomic particles, flips this logic on its head. In certain experiments, particles seem to know about their future before it happens. For example, in quantum entanglement, two particles can instantly influence each other no matter how far apart they are, seemingly violating the flow of time and suggesting that information could travel backward. This spooky action at a distance, as Einstein once called it, implies that the very structure of cause and effect might be more fluid than we ever imagined. But it gets stranger. In some cases, particles appear to move backward in time or influence events in the past. Imagine sending a signal to the past, changing something that has already happened. This is the kind of behavior scientists are grappling with when studying causality violations in quantum mechanics. The implications are profound. If causality is being violated, it could open up new doors to time travel or offer insights into the true nature of time itself. Is time an illusion, or could it be far more complex than we've ever realized? And if causality doesn't hold in the quantum world, what does that mean for our understanding of the universe? The mystery of causality violations in quantum mechanics forces us to confront the limits of our understanding of space, time, and reality. Could the universe be more unpredictable than we ever imagined? The answers remain elusive, but with every new experiment, the mystery deepens. Transplanckian Problem. In the world of physics, there's a boundary so small, so elusive, that it seems almost impossible to cross. This is the mysterious realm of the Transplanckian, the realm beyond the Planck scale, the smallest distance in the universe. Here, at length shorter than a trillionth of a second, the usual laws of physics break down, and a strange, eerie mystery begins. The Planck scale is named after Max Planck, the physicist who first proposed that there's a limit to how much we can know about the structure of space and time. It represents the smallest possible measurement of length or time, where quantum effects become so powerful that space itself may be foamy and unpredictable. It's the point at which the effects of quantum gravity, the mysterious interaction between quantum mechanics and general relativity, can no longer be ignored. So what's the Transplanckian problem? In simple terms, it's the question of what happens beyond this tiny scale. As we approach or surpass the Planck scale, our current understanding of physics breaks down completely. The mystery lies in the fact that, according to our theories, we can't even measure these extremely small distances. But what if something fundamental happens in this unexplored territory? Something that could change our understanding of the universe? One theory suggests that, in this realm, space-time could behave in unexpected ways, or that particles may lose their usual properties, making them behave in ways we cannot yet predict. Could this be the place where quantum mechanics and gravity finally meet? The Transplanckian problem remains an open question, one that could hold the key to understanding how the universe functions on the most fundamental level. As scientists push the boundaries of physics, The answers may be closer than we think. Hidden in a space so small, it seems to defy reality itself. The mystery continues, leaving us to wonder what lies beyond the Planck scale. Quantized inertia theory. Imagine a theory that could explain the forces of the universe. One that challenges the very principles of physics we've trusted for centuries. This is the premise of quantized inertia theory, a mystery that might just unlock a hidden layer of the cosmos. The theory was proposed by physicist Mike McCulloch in 2007. At its core, quantized inertia suggests a radical reinterpretation of the force of inertia, the force that resists changes in motion. In classical physics, inertia is linked to mass and is a fundamental part of how objects move. But McCulloch proposed that inertia is not just about mass. It could be influenced by the unseen energy fields in space, such as the cosmic dark energy and vacuum fluctuations that are typically considered irrelevant in most models. The true mystery begins when McCulloch applied this idea to galaxies and space travel. According to quantized inertia, objects in space may experience a modified form of inertia, which could explain phenomena like the rotation curves of galaxies, the way galaxies rotate in a way that doesn't seem to follow the predictions of current gravitational models. This discrepancy has puzzled scientists for years and has been one of the pieces of the puzzle leading to the concept of dark matter. Could quantized inertia be an alternative explanation for what's driving these cosmic motions without needing the mysterious dark matter? The theory also extends to the idea of space travel. By understanding how inertia works on a quantum level, could we unlock new propulsion methods? Could we create efficient space travel, or even harness energy from the fabric of space itself? While quantized inertia is still controversial and not widely accepted in mainstream physics, it raises an eerie question. What if the forces that govern the universe aren't what we think they are? The mystery of quantized inertia continues, challenging our understanding of space, time, and the forces that shape everything. The search for answers is just beginning. Theoretical magnetic monopoles. Imagine a magnet, a simple, everyday object. You know how it has two ends, a north pole and a south pole. Now, what if you could somehow find a magnet with just one pole? A monopole, either a north or a south, but not both. It sounds almost like science fiction, but this idea has intrigued physicists for over a century, and it remains one of the most perplexing mysteries in the world of particle physics. In theory, magnetic monopoles are particles that carry only one magnetic charge, either a north or south pole. Unlike any magnet you've ever encountered, these hypothetical particles would break the familiar rule that every magnet has two poles. If monopoles exist, they could revolutionize our understanding of electromagnetism, one of the fundamental forces of nature. The mystery of magnetic monopoles began in the 1930s, when physicist Paul Dirac first suggested their existence. According to Dirac, if monopoles were real, they could explain why electric charge is quantized. That is, why we only find electric charges in discrete amounts. In other words, discovering a monopole could give us deeper insights into the very fabric of the universe. But despite decades of searching, no one has ever found a magnetic monopole. This has led to speculation. Are they simply theoretical constructs, or could they be hiding somewhere in the universe, waiting to be discovered? Some physicists believe that monopoles could exist in exotic conditions, perhaps inside the dense cores of certain stars, or produced in high-energy particle collisions. The mystery of magnetic monopoles continues to intrigue. Could these elusive particles unlock new physics, revealing hidden layers of reality? Until we find one, The search for monopoles remains one of the great, unanswered questions in modern science, a riddle that might one day change everything we know about magnetism and the forces that shape our universe. Anomalous solar neutrino behavior. The Sun is the powerhouse of our solar system, providing light and energy that sustain life on Earth. But there's a mysterious and almost eerie aspect of the Sun that scientists have been trying to understand for decades: the behavior of solar neutrinos. Neutrinos are subatomic particles that are produced in vast quantities during the nuclear reactions inside the Sun's core. These particles travel through space, and as they reach Earth, they pass through everything without interacting with matter. They're nearly impossible to detect, yet they hold crucial information about the Sun's inner workings. For years, scientists set up sensitive detectors to measure the number of solar neutrinos arriving at Earth, expecting to find a steady flow in line with theoretical predictions. But when the first experiments were conducted, something unexpected happened. The number of neutrinos detected was much lower than expected, about 1/3 of the predicted amount. This anomaly became known as the solar neutrino problem, a mystery that has baffled scientists for over 40 years. The mystery deepened as researchers realized that the missing neutrinos weren't gone at all. They were simply changing forms. The solution came with the discovery of neutrino oscillations, the idea that neutrinos could shift between different flavors, types, as they traveled through space. Some of the neutrinos produced in the Sun's core were transforming into types that were harder to detect, explaining the discrepancy. This breakthrough was monumental in understanding both the behavior of neutrinos and the Sun's energy production. But the question remains: how does this transformation happen? And what does it reveal about the fundamental nature of matter and the forces governing the universe? The mystery of the solar neutrino behavior opened a door to a new realm of physics, showing that even the smallest particles can carry profound secrets about the very heart of the universe. And as we continue to explore these elusive particles, more mysteries may yet unfold. Levitating plasma clouds. Imagine standing in a lab, staring at a strange, glowing cloud of gas suspended in mid-air. No strings, no supports, just a cloud of plasma, levitating in perfect stillness. This is the mystery of levitating plasma clouds, a phenomenon that has puzzled scientists for decades. Plasma, often called the fourth state of matter, is a superheated gas made up of charged particles, electrons and ions, that can conduct electricity. You can find plasma in everything from neon signs to the sun itself. But creating and maintaining plasma in a controlled environment is no easy feat, especially when it starts to levitate. What makes this so mysterious is that, under normal circumstances, plasma should behave like any other gas, spreading out and dissipating. But scientists have discovered that, under the right conditions, plasma can be made to float, held in place by electromagnetic forces. This happens when powerful magnetic fields interact with the charged particles in the plasma, trapping them in a stable, suspended state. The intrigue starts when researchers try to understand how and why these clouds of plasma remain levitated without any visible support. How do these electromagnetic fields manage to keep the plasma from collapsing or escaping? And what does this tell us about the fundamental forces of nature, especially in a realm as extreme as high-energy physics? Some speculate that understanding levitating plasma clouds could revolutionize energy generation, possibly leading to breakthroughs in fusion power or even advanced propulsion systems. The mystery deepens when you consider the potential for this technology to harness energy from the very forces that govern the cosmos. The phenomenon of levitating plasma clouds challenges everything we thought we knew about matter and energy. It's a reminder that even in a world of high-tech research and innovation, there are still mysteries lurking, waiting to be uncovered. Anomalous magnetic dipole moments. In the world of particle physics, one of the most fundamental concepts is the magnetic dipole moment, a measure of a particle's magnetic properties. It's what gives particles like electrons their spin, causing them to interact with magnetic fields in a predictable way. But what if the behavior of particles like electrons isn't as simple as we thought? What if their magnetic dipole moments are stranger than we can explain? This is the mystery of anomalous magnetic dipole moments. In the 1940s, scientists began to calculate the magnetic dipole moment of the electron based on the laws of quantum mechanics. They expected it to be a certain value, which was confirmed by experiments. However, in the 1990s, a more precise experiment revealed something shocking. The measured magnetic moment was slightly off, indicating a small anomaly. This small discrepancy, the anomalous magnetic dipole moment, doesn't just suggest a tiny imperfection in measurement. Instead, it hints at the possibility that something unknown is influencing the electron's behavior. Some researchers speculate that the anomaly might be caused by new, unseen particles or even new forces of nature hidden in the quantum world. Could the electron be interacting with a new, as yet undiscovered particle or force that we can't yet detect? The mystery deepens as more experiments are conducted. Each new measurement seems to reinforce the idea that there's something missing from our understanding of particle physics. Could this anomaly be the first hint of a deeper layer of reality that we have yet to uncover? A new frontier in the universe of quantum mechanics. The anomalous magnetic dipole moment may be one of the smallest discrepancies ever observed, but it has the potential to lead to big discoveries, perhaps even reshaping our understanding of the forces that govern the universe. It's a puzzle waiting to be solved, and as research continues, the answers might just rewrite the very foundations of physics. Strange matter contagion hypothesis. Deep within the realm of theoretical physics lies a chilling and intriguing idea known as the strange matter contagion hypothesis. It sounds like something out of a science fiction movie, but the implications are very real and potentially terrifying. The hypothesis suggests that a mysterious form of matter, strange matter, could spread uncontrollably through the universe, transforming everything it touches. Strange matter is a theoretical substance made up of strange quarks, a type of particle found under extreme conditions, such as in the cores of neutron stars. Unlike the matter we encounter in everyday life, strange matter is theorized to be far more stable, with some scientists even suggesting that it could exist in a form that is more powerful and destructive than regular matter. The mystery begins with the contagion hypothesis. What if strange matter could somehow infect regular matter? Imagine this. A small amount of strange matter comes into contact with an object or particle. Instead of staying confined, it could cause the object to change, turning it into strange matter as well. Like a virus, it could spread from one particle to another, transforming everything it touches into a substance that behaves in an entirely new way. The implications are unsettling. If strange matter could spread unchecked, it might ultimately consume all normal matter, including planets, stars, and even galaxies. The universe would slowly transform into a new, unknown form of matter, governed by different laws and behaviors than we currently understand. Despite the unsettling nature of this hypothesis, It has caught the attention of scientists exploring the most extreme environments in the universe. Could strange matter really exist, and could it be capable of spreading? Or is it simply a theoretical curiosity, a scenario that could never occur? The strange matter contagion hypothesis continues to be a puzzle, challenging our understanding of both matter and the very nature of the universe itself.